Recording now. Okay. So welcome to Introduction to the Bash Shell for Data Scientists. So today I'm going to cover the basics of the Bash Shell and explain how you can leverage this kind of core powerful tool of data science to get more work done in less time in a more reproducible manner, both on your laptops and your workstations, but very importantly on Shaheen and Ibex, and also on the public cloud. So anytime you're working with remote clusters, the terminal is probably the most common user interface that you are going to have to access those systems, and Bash Shell is the language of the terminal. So if you have aspirations of doing any kind of sophisticated machine learning or deep learning training, or using GPUs on Ibex to do anything, or running high performance simulations on Shaheen, or doing any of those things on the public cloud, then you must have a good understanding of Bash. And so hopefully by the end of this, this afternoon, this 4-hour session, we will have covered probably about 95% of the commands that I use on a day in, day out basis as a data scientist to get my work done. And then I'll give you, at the end of the day, I'll give you some references and places that you can go to kind of learn more advanced tools and techniques. Okay. So the first thing I want to do is send around the link to the course repo on GitHub. So I'm going to send that around now via the chat. So if everybody could click on that link, and it should take you to, I'm going to start sharing my my screen. Okay. So if you click that link, it should take you to this repository on GitHub. So this has all of the course materials for not just today, but for the other workshops that we're going to cover in the course of the semester. So there is an introduction to Conda course that will be held next week, followed by introduction to Python, followed by an introduction to Git, followed by an introduction to SQL. And then there'll be a repeat of Python and a repeat of Conda later in the semester to kind of round everything out. And then we'll do the whole thing again next semester. So if you have scheduling conflicts this semester, we'll be offering these courses again later in the semester. Okay, so the next thing that I just want you to be aware of here is that, so for the hands-on portions of today's training, and I guess all of the trainings this semester, we're going to be leveraging a service called Binder Hub. Binder Hub is an open source project that is basically a collection of technologies that allows you to take a Git repository, whether it's hosted on GitHub or GitLab or Bitbucket or somewhere, and convert that repository into an interactive collection of notebooks that's running on some remote resources. If you're going to use the public Binder Hub, which is free, you'll be running on the cloud. But also our colleagues at the research computing, or the IT research computing, have put together an implementation of Binder Hub that is available for KAUST community members. So anyone with KAUST credentials should be able to access it. And the way that you access it is by clicking this little launch KAUST Binder Hub button here, or the launch public Jupyter Lab button here. So we're going to do some kind of quick and dirty load balancing. So I would encourage you to just kind of flip a coin, and if it lands on heads, then go ahead and right-click and open in a new tab the KAUST Binder Hub link, And if it lands tails, then go ahead and right click and open the public Jupyter Lab link in a new tab. And it may take a few minutes to spin up. But once you have spun, once it has spun up, you should see something that looks like this. Okay, so I'm going to take just a quick look at the participants. So if you go to, if you click on the participants button on Zoom, you'll see kind of a list of everybody who's there, and then some little buttons down below that you can press to provide some feedback. So I would appreciate it if you are seeing the Jupyter Lab screen in your browser now, like I have up on my screen, either from the KAUST Binder Hub or the public Binder Hub. If you could just click yes. And if you're having trouble, then click no. And this will give me some sense of basically how everybody is doing. And it may take a few minutes to load. And I've noticed, I know that today is just kind of a bit of bad timing, that there is some maintenance going on with the public Binder Hub. So you may have to reload the page, or basically just click the button again a few times in order to get it to connect. Okay. And again, just to walk everybody through, so the link that I sent through the Zoom chat will take you to the repo on GitHub. And then the buttons that you want to click are at the very top of the README file, either the KAUST Binder Hub or the public Jupyter Lab. Okay. So I'm seeing mostly non-answers. So I'll kind of assume that everybody is just waiting for it to load. But we do have a few no's. Okay, so I'm going to call on some of the no's just to kind of see what's going on. So Clara, can you unmute yourself and then kind of tell me what's going on?
Using the public one, it says starting repository is taking longer than usual to start. It's just loading and loading.
Yeah, okay.
And the other one asked me to sign in, but it's not working.
When you signed in, it didn't, your credentials were not accepted?
No, it says invalid username or password.
Yes, same problem with the Binder Hub.
Okay. Okay, well, I will have to pass that along to research computing IT to find out what is going on. Has anybody, besides myself, managed to log into the KAUST Binder Hub? If you could just unmute yourself and then just say, yes, it worked for me.
No, it doesn't work.
Okay, so we don't have anybody who has successfully done that yet.
I was able to log in the KAUST one.
You were?
Yeah.
It works also for me.
Okay, so we've got a couple people who it's working for. So the public Binder Hub, I've noticed has just been a little bit slow today. So for the moment, I will shut down the KAUST Binder Hub and I will open up the public Binder Hub. So it might sit like this for a little bit because there's some maintenance going on and it seems to be slowing down the system. But if you click on this little show button over here, you can see the logs. And so the Binder Hub has found the image that I built earlier and cached for this course today. It's just taking a little bit of time to launch. So eventually you should see launching server, and then after a minute or two, it ought to launch in the browser. So something like this. A few times earlier today, I had to refresh the page a few times to get it to load, but then you should get something like that. So if you're having trouble with the Jupyter or the Caos Binder hub, then please use the public one. And in the meanwhile, I'm going to fire an email off to my colleagues at Research Computing IT and try to figure out if there is, why it's detecting some but not all of credentials. Okay. So I don't see any more no's. Still a lot of no responses. So either some of you have just not bothered to answer and aren't having any trouble, but I don't see any more no's. So as soon as I fire off this email, then I'm just going to pick up and we're going to hop in with teaching for today. So the other link that I wanted to share is, so I'm putting a link into chat now. So the link that I am putting into chat takes you to the course webpage for today. So this is you may have already seen this. A link was shared in the original advert for today's course. But on the course webpage is basically has all of the important links, in particular the link to the course materials and kind of a summary of what we're gonna cover today. So I'm just gonna make this a little bit bigger, so hopefully everybody can read that. So today we're going to cover again kind of like the basic commands for Bash, about the 20 to 25 commands that do 95% of what you're going to need to do on a day in, day out basis with Bash. So we're going to talk about navigating files and directories, working with files and directories, and then we're going to take a little break, and then we'll probably end the day with the second half of the course will be on pipes and filters and loops and then shell scripting. Okay, so I'm seeing in chat so there's a question about can you use this on your local computer? The short answer to that is yes, you can. I've put some instructions in the README file on the GitHub repo on exactly how to do that. I'm not going to take the time to go over those instructions right now, but you can create the same environment that we're going to be working with today locally on your computer. And if you're comfortable doing that on your own, you can go ahead and do that now if the cloud resources are not working for you for whatever reason. Okay, so I don't see any more no's, so we're going to pick up and jump into the actual teaching. Okay, so as you come down the course webpage, you'll see course materials. So if you go ahead and open that link in a new tab, and I'm going to copy this link and I'll just share it in the chat for anybody who right. So these are the Software Carpentry shell novice kind of introductory to shell materials. And It's about 4 and a bit hours of content, kind of depending on how fast we go. So we may not finish all of this today, but these course materials are always online via this link, and you should be able to come back to this link and go through the materials on your own or at your own pace if we don't cover everything today. Okay. So this first lesson is going to be on introducing the shell, and it's going to be a bit more, I think, perhaps verbose than the other lessons. There's less hands-on material in this first introductory episode. And then after that, we're going to go back and forth, mostly with me sharing my screen on Jupyter Lab, and then I will continue to lecture from a copy of these notes that I have here with me on another screen. And then I'll leave you to kind of follow along with these notes yourself. Okay, so let's go ahead and jump right in. So introducing the shell. Okay. So the first thing I want to cover is basically what is a command shell and why should you use one? I mean, this is an introductory course. I have no assumptions. I don't want to make any assumptions about what you may or may not know in terms of the shell. So I'm going to assume that you don't have any background in the shell, so we're going to start at kind of the basics. So we're going to talk about the shell and how it relates to the keyboard, screen, operating system, and user programs, and also explain when and why command line interfaces should be used instead of graphical user interfaces. Okay, so some quick background. So all of us are used to interacting with computers primarily through GUIs. These are graphical user interfaces. So primarily using the mouse, these are things like point and click, drag and drop, touch screens, things like this. Our primary way of interacting with computers is through a GUI. And because of the way our brains work, GUIs are usually quite intuitive. They're very easy to learn. I got a real crash course in this when I had children, and I saw them interacting with technology at the age of like 2 and 3, and they already can kind of figure out exactly how to navigate things via touchscreen and kind of the feedback effect that they get from interacting with a computer like that. So we really have this graphical user interface approach to computing kind of ingrained in us. However, there are some drawbacks to using a GUI, and particularly if you need to do tasks with computers that are need to be repeated over and over again. It can be very inefficient to point, click, drag, drop, maybe do a little bit of typing, and then do point, click, drag, drop. It's not really well suited for repetitive tasks. It's very intuitive and quick to figure out how to do something once, but then if you want to do it, 10 times or 100 times or 1,000 times, doing things with a mouse is not great. There's a lot of lost productivity there. And this is kind of where the terminal and the shell comes into play. So the Unix shell is kind of two things. So one, it's a command line interface. So you'll hear people talk about the shell or the terminal, or I guess those are the two, or the command prompt sometimes on Windows. They're referring to the shell as like a command line interface. But shell is also a scripting language. And so there are many flavors of shell. Bash, there's just the regular shell, there's something called fish. There are a whole bunch of different variants that have emerged over the last 50 years or so that the shell has been around. But we're going to focus on Bash because Bash is kind of the de facto standard shell on many Unix operating systems. So not on Windows, but on Mac or any of the many flavors of Linux. typically bash is going to be the default shell that's available via the terminal. Now, if you have a newer version of Windows, then Windows, I think starting in maybe Windows 10, started introducing something called Windows like Linux subsystem, which has a bash terminal that you can use on your Windows machine. But if you have an older version of Windows, then you would need to install a bash emulator. And there are many kinds of many bash emulators around that you could install so that you can use bash on Windows. Okay. So let's talk about kind of the pieces of the shell. So the shell itself is a program where users are going to type commands. And these commands are usually short, sometimes only 2 letters or 3 letters, and they typically do one thing, and they do that one particular thing really, really well. These commands could be anything from ls, which is one of the first commands that we're going to learn, which basically just lists the contents of the current directory, or it could be a program that actually runs a HPC simulation on Shaheen. So these programs could be, could be very simple, or it could be very sophisticated, even though the syntax to execute the program might only involve typing a few characters. So there is a little bit of a learning curve with command line interfaces relative to GUIs. Command line interfaces are unfortunately not quite as intuitive as perhaps they could be. But if you're willing to put in the effort and kind of learn how to use these command line tools and bash, the productivity gains can be significant. You can do quite a lot with with only a little bit of typing, and you can automate repetitive research tasks and get them done more efficiently using the computer rather than using your human time to manually rerun the same kind of analysis over and over again. Okay. So the first thing that we need to familiarize ourselves is the prompt. So at this point, I'm going to kind of switch over to Jupyter Lab, and then I will continue lecturing off of my local notes. Okay, so this is what you will see if your session has timed out. So it looks like my session has timed out. So what I need to do is just close this tab and go back, and then I'll just launch it again. And hopefully it won't take quite as long. There we go. Okay. So today we're going to be using the terminal within the Jupyter Lab interface. So if you come along to the introduction of Python, and to some degree the introduction to Conda next week, and Python the week after that, we'll talk about Jupyter Lab and go into some details about Jupyter Lab and all of its bells and whistles and things like that. But today we're just going to use the terminal. So all you need to do is just click on the terminal icon, and then you'll be taken to a terminal prompt. And then I'm going to make this file pane over here go away for now by just clicking on the little folder to hide it, so I have some more space. And now just going to make this bigger. Okay, so if I type this command and hit enter, is that legible for everybody? So can I just get a quick check yes for no, or yes for no, check yes or click no, just so I can get a sense of whether this is going to be readable for everybody? I want you to be able to read what I'm typing. All right, so. Almost most of the yeses and just one no. So I made it a little bit bigger. Okay. So I'm going to type a command called clear, which is just going to clear that out. Okay. So here we go. So the first thing we want to know when we open a shell is so this blinking black rectangle is the cursor, and directly to the left of the cursor you'll see a $sign. Now that $sign is the prompt, and that's kind of the standard prompt symbol for Bash. Other flavors of shell will have maybe different prompts. Windows uses a different prompt, but $sign is the prompt for Bash. Right. So at the prompt is where you're going to type commands. So the first command that we're going to type is the command ls. So if I go ahead and type ls and then hit enter, then you'll see some output. And this is the typical way that we're going to work with the shell. We're going to type a command, we're going to hit enter, and then we're going to get a response. And then as we get later in the day, we'll talk about how to do things like redirecting output to a file. So instead of seeing output here on our screen, it'll get redirected to a file, and some other ways to kind of interact with everything. So what we're seeing here is a listing of all of the contents of the current directory that we were in when we opened the terminal. So if I just go over here and click on this little folder, this directory, then you can kind of compare the GUI interface, and you can see here like there's these different directories: assets, bin, Docker, introduction to, a bunch of different ones, and then some files and a license. So that's kind of the GUI version of what we have there. And then for the command line version, you can see what we have on the right. You can see that it's the same. So I'll make that go away just so we have some more space. Now, some versions of shell have some nice syntax highlighting. Not all of them do. So here, what we can see from the colors is that anything in just plain black text is a file of some kind. Anything that is blue, light blue, is a directory. And then anything that's green is an executable. And we'll talk a little bit more about executables later on today. Right. So so what happens if we make a mistake when we're typing a command? So if we typed ks and hit enter instead of ls, so ks is not a valid bash command. So this is the error that you get. It'll just say, this is actually the name of the program that ran the command or program ks. Bash, that's the shell that we're using. Ks was the command, and this command was not found. So it just returns this error. So that is basically the typical error that you will see if you just mistype a command. Okay. So I'm going to flip back to the course lecture notes for a minute and just give a little bit. So that was just a quick introduction to kind of the background of the shell. We just talked about like the shell prompt, typed a command, hit enter, kind of got a feel for what's going on. So the way that I'm going to kind of motivate the rest of this afternoon's workshop is around this kind of hypothetical marine biology research problem. And so we're going to follow kind of the research journey of Nell Nemo, who has collected a bunch of survey data from the North Pacific Gyre, which is, I mean, you can click on the link and I think it takes you to the Wikipedia page, but it's basically the location in the North Pacific where all of this garbage ends up because of the natural current patterns. It pulls all this garbage kind of from everywhere in the Pacific, even from Asia and all the way over, and just kind of sucks it into this gigantic garbage patch. And so she's gone up there and taken some physical samples, and now she's come back to her university, and her university also has some lab machines, just like we do here at KAUST, and she has these 1,500 samples, and then she needs to run them through this machine, which is then going to take a bunch of measurements and spit out a bunch of data. And then she's going to need to do analysis on that data. So our 1,500 samples are going to go through this physical machine. It's going to generate measures of relative abundance of 300 proteins. Then she needs to take each of those output files. So there are 1,500 output files, one output file for each of the physical input samples. And then she needs to run it through this the statistics program that she inherited from either her PI or a previous student or postdoc that worked in that research group. And so she's got to run this statistics program for each of 1,500 samples. And then she's got to write up all the results, and then they're going to submit a paper. Now, the idea is that this research kind of workflow should seem relatively familiar for many of you here at KAUST. Certainly if you're doing research, you might not work necessarily with physical samples and physical machines to generate your primary research data. But you can, I'm sure, appreciate the idea that you might have lots of individual data files lying around that you need to analyze. And it would be great if you could learn how to systematically automate all of these analysis tasks so that you could maximize the amount of work that the computer does and minimize the amount of time that you have to manually do stuff, because you have other important things to do, like, you know, go for coffee, hang out with your friends, go snorkeling, all these other things. You want to make the computer work for you, so you don't have to use your precious time doing repetitive tasks. So if you're going to do this by hand, then, you know, if your GooStats program, if you're going to do this by hand, you have to manually select the file and maybe drag and drop it into the GooStats GUI, maybe do a bit of typing, hit enter eventually, and GooStats might take 30 seconds to run each file. Then if you were doing this manually, then that's basically 12 hours of your attention, of your eyeballs on the screen, kind of paying very close attention to what you're doing. And that assumes that you don't make any mistakes, that you're able to kind of keep up. Every 30 seconds you're running another file, one after the other for 12 hours. I mean, that's like, you can't really do that, So instead, we're going to see how we can automate this workflow using Bash. And we're going to do that with for loops and see how we can basically get the computer to do all this work for us. And then at the end, whenever you automate something, a very important benefit that you get is at the end you'll have a script, and this script will basically be able to reproduce your entire workflow from start to finish. So not only will you get more done by automating these kinds of tasks, but it will be more reproducible, because you'll have a record that can just be rerun from start to finish and just redo all of your analysis. Okay. So just some key points to sum up before we move to the next episode. So the shell is a program, and its primary purpose is it reads in commands and runs other programs. So it's a way to interact with the computer with text and get it to do stuff. So the main advantage of the shell is that it's super productive in that you can do quite a lot of work with very little to minimal typing. It's great for automating repetitive tasks, and it allows you to access remote machines, again, like IBEX or Shaheen or public clouds, or I'd say a major advantage that my skills with the shell has allowed me to take advantage of logging into my workstation in my office in KAUST from my house, which is where I'm I'm teaching from at the present. And that's been amazing because I had a whole bunch of work that was sitting around on my workstation that I basically just had to leave there when we started working from home. And now I can basically log into that machine remotely, and it's as if I was just sitting at my desk, and I can use not only the nice computing resources that I have on my workstation, but also all of my data, all my research projects. As long as I have a network connection, I can do my work via Bash and via the terminal. Okay, so I'll just open it up real quick for questions. So if anybody has a question that they would like to ask, then please unmute yourself, and I will try to answer it. Or actually, I totally forgot about the question link. So back on if you did have a question, I will come back to you and then give you another opportunity to answer. But on the workshop repo, there's a little button here that says Gitter join chat. So if you open that in a new tab, and I'm just going to copy this link and send it around in the chat. So if you click on that link, then eventually you'll end up, this link has been slow today for reasons that I don't quite understand. But eventually it will load. Okay, well, while it's loading, if you have a question, you want to unmute yourself and ask it, then please do. Okay, so it's just me. So Mohammed says that the link works fine and is reasonably fast. So it seems to be just me for whom it is going slow. Maybe I should turn off my ad blocker. Okay, well, when it loads, this is basically like, it's a Slack, like Gitter is an alternative, it's an open source alternative to Slack, basically, where instead of being very focused around a company, it's more focused around you as a participant in a community. So basically, in like Slack, you have a separate profile for each Slack workspace that you're in. With Gitter, there's just you. And then you can interact with different Gitter chat rooms. I've created a chat room. Here we go, finally loading, for the Introduction to Data Science workshop series. And so on the left-hand side, so you should see the link should take you to this landing page for the Introduction to Data Science workshop community. Then on the left-hand side, there should be an introduction to Shell. So if you click on the introduction to Shell, and I'm also going to post that link there. Yeah, so you will have to have, not an account necessarily with Gitter, but you may have to have like a GitHub account. So you can sign in with GitHub or GitLab if you have an account. If you already have an account, then you can sign in and participate and kind of post your questions there. And then I will try to monitor and answer them, even if I answer them kind of afterwards, after the course is done. But it's being really slow to the point of not really being usable today for me. It seems to be working for others, but for me, it's super slow. So I will answer any questions basically there that are posted. So these are some questions that were posted back in June from the last time I taught this course. So I will kind of continue to to answer questions here if you post them. Okay. So I'm going to go back here and just hit enter to make sure my instance doesn't die. So I haven't heard or seen anybody pop up with a question, so I'm going to go ahead and move. I'm going to go ahead and move on to the next episode. Okay. Okay. So the first thing that we're going to talk about is navigating files and directories. So this is answers basic questions like, if you're not going to use a GUI, you're not going to use a mouse to drag and drop and point and click, how do you navigate? How do you move around on your computer? How do you see what files and directories that you have? If you're using a GUI, of course, you can see the folders, and you can click on a folder, and then you can see the contents of the folder. But how do you do that if all you have to interact with is the terminal and some commands? And then how do you refer to the locations of files or the locations of directories on your computer? So the key objectives that I have for you for this episode is to be able to explain the differences and similarities between files and directories, understand the two kinds of paths that you have. You have absolute paths and relative paths, and understand how to translate from an absolute path to a relative path and vice versa. So that's a really key learning outcome for this episode. So you're going to see some examples, and you're going to have some exercises to construct absolute and relative paths in order to identify files and directories. Understand what options and arguments are and how they can be used to change the behavior of a shell command. And then demonstrate the use of tab completion and be able to explain kind of why tab completion is useful. Okay. All right, so here we go. So we're going to go back to Jupyter Lab. I'm going to get my teaching notes up on my other screen. Okay. So, so the part of the operating system that is responsible for managing your files and directories, so this is what's called the file system. Okay, so a file system organizes data on your computer into files which actually hold information, and directories or folders which hold files, or sometimes other directories. So what we want to learn are commands that we can type here into the shell that will create, inspect, rename, and delete files and directories. And so that is going to be our kind of point of departure for this. So the first command that we're going to learn is basically, where am I? So what directory am I currently in? So let's learn how to do that command. So that command is pwd, which is short for print working directory. So if you hit enter, then we'll see that we're in this directory called /home/Jovian. So this looks like a user home directory, and that's exactly what it is. So here, if you're running on Binder Hub, Jovian is the user that has been created for, the anonymous person who's basically running their code on Binder Hub within Jupyter. Right. So this is what a home directory kind of looks like on Linux or on a Mac. On Windows, home directories look a little bit differently. You might be used to seeing something like C:/ documents and settings / then your username, or something like this. Right. So let's try to understand a little bit more about how things are organized. So again, pwd is the command that kind of prints your working directory. So a typical file system is going to look something like this. So you're going to have a slash, which refers to like the very root of your file system. And then within that, you're going to have some directories. There might be a bin directory for binaries. There might be a data directory, a users directory. If this is a computer, if it's a computer that has multiple users, then each user will have its own home directory inside of users. There might be a temp directory, which provides some temporary storage space for users on the system. But the important thing is at the top, there's this slash, which represents the root directory. And it's that root directory that holds everything else in the file system on that computer. And it's usually referred to as a slash. And so inside that directory, there's going to be many other directories. And then on our Jupyter Lab, we can follow from the root of the file system down into the directory home/Jovian to the directory that we're currently in, which is that particular user's home directory. Okay. So now, again, if we run the ls command, we're going to list everything in the home directory. And so we've got files and folders, just like we mentioned before. Okay. So results, if you're running this on a local machine, you might get different results because everybody's user home directories on their laptop or the workstation is going to be different. Here it should be basically identical as long as you're running on Binder Hub. Then we're running off the same set of materials, so we'll see the same thing. So next, we're going to learn our first option. So if we type ls space and then -F and hit enter. So notice that the output is now different. So all of the directories end in a slash, like a slash there. Nothing seemed to happen to the text files, but then this executable file got an asterisk after it. So here we've got some nice syntax highlighting, but if you're working on a remote machine that doesn't support syntax highlighting, I do not believe that IBEX certainly, and I don't know about Shaheen, but also probably not. I don't believe that there's syntax highlighting on those shells. So then the way that you would differentiate as to whether something was a file, a folder, or an executable is by running ls with this -F command, and then that will put slashes after any directory and stars after any executable. Okay. Now, if your terminal starts to get kind of filled up with commands, there's another command called clear, which you can use to just clear out your shell, and that will just kind of clear everything out and give you a kind of a new space to work with. Okay, so now let's look at the kind of the general syntax of a command. So we're going to start with our command ls, and then we're going to have a space, and then we're going to put an option. So -F is the only option that we know at present, and then we're going to put another space. And then we're going to put an argument. In this case, we're going to put a single slash. So that command with that option and that argument is going to list the contents of the root directory of the file system, which is what's represented by that slash. And then it is going to put slashes next to any directory and stars next to any executable that it finds in that root directory. And that's what happens when you use the -F option. Okay, so if we hit enter, we'll see there. And you'll notice that, perhaps unsurprisingly, in the root directory of this instance, of this remote computer that we're working on, is a whole bunch of other directories. I should note, so sometimes these options, you will have a short form and a long form. So the short form of an option is a single dash and usually a letter, could be uppercase or lowercase. The long form of an option, if it exists, will always have 2 dashes, and it will be followed typically by like a full word that usually starts with the same letter as the short form of the option. Also, sometimes arguments are referred to as parameters. So you might run into that kind of different nomenclature. Okay. So again, notice that each part is separated by spaces. So that's important. So if we try to do ls-f without a space, Bash is going to interpret that whole sequence of 4 characters, ls-f, as a command, and then it's not going to find that command, so it's going to give you an error. So the white space is important. So in the teaching notes, it talks about a couple of other options. So there is an ls-s, lowercase s, and so the lowercase s displays the size of files, but here it's not really giving you obviously useful information. We'll see a better way to get the size of files in a minute. But actually, if you do -capital S and the slash, you'll see that it ordered the files and directories by size, which is not at all obvious. But the point of this is just that they're case sensitive. So sometimes the same option in lowercase versus uppercase is going to do something that's completely different. So just be aware of that. So at this point, you might be wondering, well, how on earth do I know like what options are available or what the appropriate syntax is for the command, or like other than Googling or something like that? How do I know any of this? Well, most commands will have a help menu. So if you type ls, and maybe usually there'll be a short form, maybe a -h, which does something different for help or for ls, but so you need to use a long form --help. I always use --help because it's consistent. You can use it for all the commands. And if you type --help, then you get the manual basically for ls. And you might think, well, gosh, listing the contents of a directory seems like a pretty straightforward thing. How many options could it have? And obviously the answer when you look at the help menu is quite a lot, right? So just kind of glancing through here, almost every letter in the alphabet corresponds to some option of the ls command. And you can see here, like, this is an example of an option that has both a short form and a long form. So -r or --reverse reverses the order while sorting. So it will, return the outputs of the listed contents of the directory sorted in reverse, basically. There's another option. R does something completely different. So R or --recursive lists not only the contents of the current directory, but recursively goes through and lists the contents of every directory inside the current directory until it just lists files, and then it stops. So if you ran this command, so I'm going to clear this out again. So ls-r on the root directory, so that would recursively list every directory on the file system until it hit until it hit a directory containing all files, and then it would go back up and would just continue until it had listed all the files on the computer, which might take quite a while. So I'm not gonna run it. Okay. So we saw all the help options. Okay, unsupported command line options. So the next thing in the notes, so it looked like most every letter in the alphabet was an option for the list command, but actually it's not quite right because -J is not an option. So this is kind of an example of what you'll get, what the output will look like if you specify an invalid option. You'll be told that it's an invalid option, and then you'll be given a hint, basically read the manual and find out what options are valid and what options are invalid. The teaching notes mentioned something called a man page, manual pages. They are not, for technical reasons, they're not available on this cloud instance, but they would be available on Ibex or Shaheen, or if you're running a terminal on your local workstation or laptop, the man pages will be there. And so you could do, you could follow the examples in the teaching notes as an alternative to get help. And then there's some links in the, there's some links in here to manual pages on the web. So you can click these links and follow them if you want to read if you prefer to read the documentation online. So all the documentation that you can access via either help or the man commands via the terminal is basically available as a web page. So once you know what command you're looking for, you can go to these websites and basically look it up and read it on a browser if you would prefer to do that. Okay, so there's a couple of exercises here. So what I want to do now is take a couple of minutes. So I'm going to set a timer just for 3 minutes and give you guys an opportunity to play around with these exercises. So exploring flags with LS, and then doing some reverse chronological order listing, and see how you get on. In the meantime, I will check if there are any questions in chat or if there are any questions on the Gitter page, and I will try to answer them, and then we'll come back. So I guess something else I should say is that the solutions to all the exercises are available, and you're trying to do the exercise before you actually click on the down arrow to see what the solution is. You will learn quite a bit more that way than you would if you just go ahead and jump ahead to the answers. How do you exit man ls on Mac? I believe you want to type Q. So, yep, so that's here. So there's a question in chat about how, if you get stuck in the man page, how do you exit the man page? So in the lecture notes, the man command, it kind of explains that you can toggle through the output using the up or down arrows, or spacebar or B key to kind of skip backwards and forwards. And then if you want to quit, you can just press Q. All right. Not seeing any questions showing up in good question. So how can you force interrupt a command? So So the way that you force interrupt a command is with Control C. So this is useful if you get yourself into a command that's just spewing lots of text to the screen and you just want to kind of kill it and stop it from running. You can hit Control and C. And yeah, so the Gitter chat is really unusable for me. Maybe I will need to update my browser, in which case I will go back and do that during our kind of mid-afternoon break. Okay, so there is a 3-minute timer. So you don't really need to post. So there's a question in the chat about posting the solution. So you don't really need to post the solution. You know, I'm not grading these in any way. So don't worry about posting the solutions. Okay, so let's take a look at. I'm just going to do one of these now because the solutions are there. So we'll look at the first one, which is, so what does the command ls do when you pass the -l option? So if we do ls, so first let's just clear this out. And then we'll just type ls -l, and then ls-lh. And so this would be the first example of passing multiple options. And you can just pass multiple options with a single dash and then the option. You can probably also do this. Yeah, so you can pass each one separated by a space if you want, but what you'll typically see is just a single dash followed by the individual characters for the options that you want. All right, so let's look at this. So the first command, just ls by itself, we've seen this many times. It just lists the contents of the directory. Now the ls-l command, what did this do? Well, it gave us not only a different format of the output, it gave us quite a lot more information about the individual file. So on the far left-hand column of the ls-l output, you get the permissions for the file. And without going into too much detail about file permissions, which is a more advanced topic that's kind of outside of scope for this particular course, basically every file or directory can have read, write, and execute permissions, and then those permissions can be further distinguished between whether the user of the computer can read, write, and execute with that file, or the group that that user is a member of can read, write, and execute, or whether anybody who has access to the machine at all can read, write, and execute. And this is kind of each of these little letters and their sequence kind of tells you what the permissions for that file or directory are for the world, the group, and the user. But we won't go any more detail than that. And then here you have the user and group, which are basically the same, Jovian and Jovian. Here, this column, which you can see is actually slightly different in the last output, this is actually an indication of the size in bytes of the file or directory. And then you have a timestamp. So this will be the timestamp at which the file was created. So you can see the timestamp at which I built the image of this that we're using today was at 6:50 this morning. So I was working on this quite late to get it ready for teaching materials today. And then of course, then we have the actual files and directories at the last column. Now, this size of the file in bytes, 10, 4096, 12, 257, like that's not really something that's very human readable. We tend to think in terms of like maybe kilobytes or megabytes or gigabytes or petabytes, things like this. So if you put the -H option, it's kind of short for human readable. And then that is what actually provides a more human readable indicator of the size of the file. So this file, the app.txt file is 10 bytes. The README file is 12 kilobytes. There's nothing, your data files might be megabytes or gigabytes, depending on what you're doing, things like that. So I'm gonna clear that out. Okay. All right, so exploring contents of other directories. So far we've basically just done something very specific, which was list the contents of the current working directory, which we got by typing pwd. All right, so what if we want to list the contents of some other directory? So let's see. So what other directories do we have? Well, we have this introduction to shell, so why don't we list that? So if we list the introduction to shell, you'll see inside the introduction to shell, there is a data directory. So let's keep going. So let's list the introduction to shell / data. Now we're getting something more interesting. So inside the data directory, there's a creatures directory, a data directory, molecules directory, some files, some things like that. Okay. So what if let's practice our options again. So we can do ls-f, -f. And notice I did something there. I pressed the up arrow. So if you press the up arrow, you can toggle through the history of commands that you've typed. And the down arrow will toggle back. So that was how I was able to quickly just retrieve that previous command and then add a -f. And so that tells us that we've got these directories in there and then a few files. Now, it's a bit tedious listing the contents of other directories from wherever the current working directory is or from your user home directory. So we want to know how to basically change directories. So that's going to be the next command. So the command to change directories is cd, short for change directory. So if we change directories into introduction to shell / data, now we've changed directories into the directory that we specified as the argument to the cd command. Right. So notice that the prompt changed. Now to the left, so previously to the left of the prompt, we just had this little tilde symbol. And the tilde symbol is actually a shorthand syntax representing the user home. So that's another important thing to remember. The tilde represents your user home. But then once we change directories to this introduction to shell / data, now to the left of our prompt, the $, we have the tilde representing our home directory / introduction to shell / data. So it's basically telling us in the prompt kind of where we are relative to the home directory of the user. And that's very common. You'll see that on Ibex and Shaheen as well. Okay, so if you type pwd, so now we get a different output. Before we just got the home directory, now we get the absolute path from the root of the file system / all the way through to the current directory, which is now data. Okay. So let's see if we can go even further. So let's list the contents of the data directory. So now we have this other data directory here. So let's see what's in that. So we'll do ls-f again on data. Okay. So it looks like in this data directory, we have a bunch of text files, some animal counts directory, elements directory, PDB directory. So this looks like some raw data. Okay. So, but let's suppose, and we can change directories into this directory. So if we go say cd data, then now our prompt has changed again. So we've got introduction to shell / data. And if we just run ls without any arguments, we'll put a -f option, we get the same results as we got when we ran this command before we had changed the directory. If that makes sense. Okay. So the question in chat about the command for opening a PDF file. So that's an interesting one. So if you, depending on like, what do you want to do with a PDF file? So open the, when you're working with the terminal, you open files and do stuff with them in the terminal, but you don't really open a PDF and like look at it because you don't have, there's no screen or anything to look at. So you could, pass a PDF file as an input into another program from the terminal, and that might do some processing on that PDF file. Or if you really know what you're doing, you could use the shell to open a PDF file from a remote machine inside the browser on your local machine. But that requires some advanced concepts that are outside the scope of this course. Okay. So this whole time that we have been changing directories, we've kind of been moving down the file system hierarchy. Like we started in the home directory, then we changed directories into these two directories that were subdirectories in the home directory, and then we went even further down the hierarchy. But what if we wanted to go basically back up the hierarchy, back up the file system? So we wanted to go back to our introduction to shell data. So if we tried to do something like this, so this is the name of the directory where we were before. So if we try to do this, we get an error. And the error might seem a bit cryptic at first. It says no such file or directory, but we're like, well, wait a minute. There is a directory called introduction to shell. We were in that directory earlier, so why can't we go back to that directory like this again? And the reason is that the cd command only sees directories that are further down the hierarchy than the current directory. So it sees the contents of your current directory, but it doesn't see kind of what's above the current directory. So so what's the solution? Well, the solution is a special directory reference called .. And it kind of stands for the parent directory of the current directory. So if we do cd .. Now look at our prompt. So now we've gone one level up in the hierarchy. We've gone to the parent of introduction to shell /data/data, which is introduction to shell /data. From here, we can go up another level in the hierarchy to that parent directory, which is the directory that we wanted, which is introduction to shell. So this .. is kind of a special directory reference, which kind of means like the directory containing this one, or the parent of the current directory. Right. So how did I know to do this, besides the fact that I teach this course and I've taught it many times? Like, how did you know that this .. existed? Like, surely there should be something that is in the current directory that tells you that this thing exists, and there is. So if we go back to the list command and we look at the help menu, the very first option is -a, the short form, or -- all, the long form. So, and it says, do not ignore entries starting with dot. So by default, a lot of commands will ignore files or directories that start with dot because the interpretation, the convention is that such directories are, quote, hidden or private. But hidden is probably the more accurate term. So if we run our, if I clear this out, and if I run the ls command with the dash a, f, well, let's just do it with dash a first. We'll see that not only do I have the data directory, but now I have these two special directories, dot and dot dot. So if we run ls-af, we can see that we have a dot slash and then a dot dot slash. So we can see that those two things are directories. The single dot is a reference to the current directory, and the two dots is the reference to the parent directory. So those are two special directories. The dot dot is very useful because it allows you, it's what allows you to basically use CD to go back up the hierarchy. But the dot is also useful. We'll see it again later this afternoon. And you can think of the dash A as kind of a shorthand for show all, or okay. So other hidden files. So other than the hidden directories dot dot and dot, in your home directory. So if we, well, I'll teach you another shorthand. So if you do CD without any arguments and hit enter, where does it take you? Well, it goes back to now to the left of the prompt is just the tilde, which is the shorthand for our home directory. So CD with no arguments will always take you home, takes you back to your home directory. So if we run ls dash, let's just run ls on the home directory. So we get this again. If we run ls dash a, we get a lot more stuff. So what's going on here? So these are all examples of either hidden directories or files. So a couple that are relevant. So here you'll see this .bash rc. So that's your a special bash profile file for interactive bash shells. And then there's a .profile, which is a special profile for something called login bash shells. And then there's a bash logout, which is a special file that has things that can be done on logout. So those three special files are how you can configure your user bash profile to do all kinds of things by default whenever you log in to different kinds of shells or when you log out. These are important things to be aware of because when you're working on Ibex or Shaheen, users will often try to customize their user experience a little bit on those remote servers by making changes to these files. .Jupyter, so this is a hidden directory if you've got a Jupyter lab or Jupyter notebooks installed on your computer. .Jupyter is where a bunch of configuration files for those things go. There's something called a .cache directory, which has which can sometimes cause weird behavior if things get cached there. If you install software on, say, Ibex via pip, in particular, has a nasty habit of caching things in that directory that will lead to funny surprises. Conda, so this is for the Conda package and environment management tool. All of the special Conda configurations and things like that are in that directory. If you come next week, we're going to have a whole afternoon on Conda to discuss how to use that. Very powerful tool for working, building software-specific or project-specific software environments. So yeah, so lots of hidden stuff in your home directory that you can look at by with this -A flag. So there's a question on chat about how you delete entire files or directories. We're about to get to that. I'll try to pick up the pace a little bit. Obviously, feel free to work ahead if you wish. The entire teaching materials are there, so you can just plow on ahead if you feel so inclined. Okay. Right. So let's go back to the teaching notes and kind of see where we are. So we did hidden files. Okay, so we've covered 3 basic commands for moving around on the system. pwd, which is kind of where am I, what is the current working directory. ls, which shows you the contents of the directory. cd, which shows you how to kind of move around the file system on its own. And we've done some examples like this, so I'm going to skip ahead to the exercises. So I'm going to set the timer again for 3 minutes. So if you could just take a look at these exercises, the absolute versus relative paths, relative path resolution, and some reading comprehension on ls. And then I'll pick one of them to kind of go through together. And then I'll check the chat or the chat for questions. Okay, so deleting entire files or directories. So that was a question in chat. So yes, the command is rm, and the reason I didn't respond is that there are some subtleties and danger zones with deleting files and particularly directories that you need to be aware of, and I kind of want to cover those slowly. Rakesh has a note about being careful with the rm-r command, and that is very true. If you're not careful, the rm-r command can completely delete the entire contents of your computer's file system. And it's a great example of, Bash is very powerful. You can do quite a lot with a relatively simple command, but with great power comes great responsibility. And if you don't know what you're doing, then you can very quickly do something that you really didn't intend, like accidentally delete your home directory on ibex or something like this. Or even worse, accidentally delete your project's data directory, which is shared by you and the rest of your team, including your PI, on your ibex Scratch, project Scratch allocation. Please keep the questions coming on the Zoom chat. That seems to be the best mechanism today. If you have any questions, I'll try to repeat them and then answer them. And then, of course, I will go back to Gitter and answer any questions that are posted there on Gitter once I figure out why my browser is so slow. Okay, so there's my my timer gone off. All right, so let's take a look at this exercise right here, this reading comprehension, and then I'll go back up to the absolute versus relative paths. So in the file system diagram below, if pwd, so that's the command that displays the current working directory, users/user/backup. So that means that we are in this directory here. And then -r tells ls to display things in reverse order what command will result in the following output. So if we want, so first note, we have these trailing slashes. So that means that we must pass a -f option, because that's how you'll get those trailing slashes. And so we can look at the answer. So ls on pwd is just going to list out the 3 subdirectories without the trailing slashes, but in alphabetical order. So, or it will be original, PNAS final, and PNAS sub. And so if we want to reverse that, then we need to pass the -r flag. So 2 would work. And notice that since we're not passing an argument, it will default to the current working directory. So that's fine. But we can also pass the absolute path from the root of the file system down to users and backup, and that will give us the same answer. So I would say 2 and 3 will both give you the same answer. Now let's go back up here. So relative path resolution. So is this one or? So we'll do kind of both of these because it touches on the difference between absolute versus relative path, which is important. So if you're in a directory /user/amanda/data, so which of the following could you use to navigate to your home directory users Amanda? Well, so the first option, cd dot. So dot represents the current working directory. So cd dot isn't going to do anything. It's just going to leave you in your current and in the current directory. cd slash, well, slash again is the root of the file system. So that's going to take you all the way back up to the root of the file system. cd/home/Amanda. So this file path starts with a slash. So that indicates that it's an absolute path from the root of the file system down to the user's home directory. So that's fine. So that will work. So 3 is correct. ///. Well, that one looks a bit complicated. So what's that one doing? So cd ... takes you from your current directory back to the parent directory. So .. might then take you one more level up in the directory. So that will take you from data to Amanda's parent, which is users. So that's one level too far back. cd tilde. cd tilde is, so tilde is the shorthand notation for the user's home directory, so that will work. cd home is going to look for a directory called home inside user/Amanda/data. So that's not the right answer. 7 is, this is getting complicated. So cd tilde home directory /data, so that's where we currently are previously, /.. which is go back up one parent or to the parent. So 7 is actually correct, but it's a really convoluted way to accomplish the task. And then 8, of course, 8 is also correct. So cd with no input will take you from your current directory back to your home. In this case, cd ... takes you up to the parent, which is also correct. Cool. So basically, if you can walk yourself, if you kind of understood the explanations that I just gave for each of those 9 options, then, and you can look at the explanations here, then you have a good understanding of the difference between absolute paths and relative paths. And again, absolute path is a path that starts with a slash and goes from the root of a file system down to some file or directory. Whereas a relative path is a path to a file or directory relative to the current location, the current working directory. Okay. So there's a question about how to create directories and how to create hidden directories. And we'll see how to create directories. That's the very next thing that we're going to talk about in the next episode. All right, so we're going to hop back over to Jupyter Lab for a minute. So we're going to take a look at, where am I? So PWD. So I want to go to CD introduction shell / data. Right. Okay. We did absolute relative paths. Okay, so we can see I'm just going to talk you through the files that are here in Nell's research data folder. So this North Pacific Gyre directory. So we can take a look at what is in this North Pacific Gyre directory. And notice I've been kind of doing this without talking about it, but I've been using tab completion. So tab completion is a way to avoid silly typos by you basically type the stem. So in this case, the simplest stem could be maybe N, and then you hit tab. And then notice it completed NO. Well, that was the common stem between the two things that started NO. And then if you hit tab twice, you'll be given a list of things that match that pattern. And if you keep typing and hitting tab, as soon as you've uniquely identified the file or directory, tab completion will just immediately auto-complete the rest. So again, tab completion is really handy. I would encourage you to use it. If you're like me and very prone to silly typos, then it'll save you a lot of time and effort. Okay, so let's just take a look then at what is in this directory. Okay, so there's a timestamp. So kind of a small tip on your research. So if you name directories with timestamps in them, make sure that you use leading zeros. So like 07 for the month and 03 for the day, not just 7 and 3. The reason is that if you use the leading zeros, then the files will automatically be sorted correctly in chronological order. Whereas if you didn't put a leading zero, then October would come before June and July and things like that, and it would just be out of order. So use leading zeros when you're working with dates. If you're using dates in your file names. So what is in this directory? So inside this directory, we have these two executables, goodiff and goostat. So here they're green. But if we did -F, we would see the little stars indicating that they're executables. And then we have these text files. And these text files look like they're structured in a nice way. And they look like they have some kind of useful coding. They all have the same extension, .text. Then they all have either an A or a B, it looks like, although here's a Z over here. So these, basically these are supposed to be the text files that were generated from the assay machine that the physical samples were let into. So it's very common for data generated by lab machines to have some structured file naming convention that is used. And these structured file naming conventions are nice because they can be exploited via a technique called pattern matching that we're going to talk about in a little bit. Right. Okay. So just wrapping up. So we covered kind of how to move around the file system and how to inspect the contents of directories. So we covered CD, which is how you navigate around directories. We talked about how CD can move down the directory by just specifying the directory or the directory in the current directory that you want to move into. But if you want to go up in the hierarchy, you either need to, you typically will use the ... to move up to the parent. But you can also pass, instead of those relative paths that instead of passing paths that are relative to the current directory, you can pass in an absolute path, which will always start with a slash, but then will uniquely identify the directory in the file system hierarchy that you want to move to, and then you can change directly to that path. So the slash by itself is the root of the whole file system. And again, these are the important things. A relative path specifies a location starting from the current location, and an absolute path specifies a location from the root of the file system. So those are the two differences. Okay. So let's go ahead and move to the next episode. So working with files and directories. And so the questions that I've seen in the chat are basically answered in this episode here. So how can I create, copy, and delete files and directories? How do you edit files? And there are some exercises that allow you to practice using these commands to create directory hierarchies that match a particular diagram, and create files by using an editor. So we're going to see how to use a text editor directly from the terminal. And then there's some exercises on deleting, copying, moving specified files and directories. Okay, so I'm going to go back to Jupyter and clear all this out. And it will stay in the data directory. Okay, so creating directories. So let's run pwd, see where we are. So we're in our introduction to shell / data directory. And then we can again run ls-f to see what is there. Okay, so let's suppose we want to create a directory called thesis. So the next command we're going to learn is make dir, nkdir, which is shorthand for make directory. And then we'll type the name of the directory that we want to create. Make dir thesis. And now if we run ls-f again, we'll see that now here's this thesis directory which we just created. Right there. So there we go, not so bad. Make dir. If we wanted to kind of get a sense on the GUI, so if we opened up the GUI and we navigated with the mouse into introduction to shell, into data, so here's this thesis directory. Note that it said last modified seconds ago. So there's here the basic idea is that if you were to create something via the GUI or create something using the make dir command, is two ways of doing the exact same thing. Now, since JupyterLab is itself a GUI, we could go up here to this little folder with a plus on it and create thesis2, and then go back over here. And now there's thesis2 is now showing up in the contents with list. So again, just two ways of doing the same thing. All right, I'll make that go away now. There's a question in chat. What if you misspell the name of the directory? Is it possible to rename? Yes, it is. We're going to talk about this command. It's further down in this episode, but a preview of coming attraction is that the command to rename is actually nv, which is move. So you rename things by moving them to a different location in the file system that has a different name, basically. But we'll cover that specifically in a minute. Right. So we did creating directories, two ways of doing the same thing. Okay, so conventions for, now we know how to create files and directories, some conventions, good naming conventions for files and directories. So do not use spaces. White spaces in file names is a big no-no, should be avoided at all costs. It kind of crept in via Windows usage, where it's quite common to have spaces in file names. But you should avoid it. That's, a big takeaway in some sense from today is please avoid spaces in your file names. It'll save you a lot of trouble later on. So if you want to use something like a space, prefer a dash or an underscore. I prefer underscores, or I prefer dashes to underscores, but pick one and be consistent. So north dash Pacific dash gyre instead of north space Pacific space gyre, as an example. So don't begin file names with dashes. The reason for that is that Unix commands treat leading dashes as options. So if you tried to, create a file that started with a dash, Shell would probably interpret that file as a list of options, and then it would just do something undesired. So the things that you can include in file names and directories are period or full stop, dashes, underscores, letters, and numbers. Don't use special characters like @ or $, or things like that. They typically have special meanings in bash syntax, and weird things might happen. If you find yourself needing to refer to files and directories that have spaces or special characters in the file names, then the way that you handle that is by putting double quotes around the thing, and that will kind of force bash to interpret it literally, including the white space. Right. Okay. So let's go back here. So if we were to run ls on the thesis thesis directory that we just created, of course, there's nothing there, so we don't get anything back. Except if we were to run ls thesis -a to show all, we'd get dot and dot dot. Dot and dot dot are always there. Okay, so let us create a file. So we created a directory, so let's create a file. So if we change into the thesis directory, and now we're going to make a text file called draft.txt. And to do this, we're going to use a command line text editor called nano. So nano is going to be the name of the program, followed by a space, followed by the name of the file that we want to create, which is draft.txt, and hit enter. Now, this has dropped us into something called a buffer. This is so the nano program has taken the input draft.txt, which is a file name that we want to create. Now it's dropped us into a buffer where we can type things. So if I wanted to follow lecture notes, we could type something like, it's not publish or perish anymore. It's share and thrive. Thrive. Enter. Now, how do I get out? I've typed some stuff that I want to type. And now to get out, I need to use some keyboard shortcuts. So at the bottom, this caret symbol is short for control. And then you can see there is different options. So control X for exit, control O for write out. So if I do, let's say, control X for exit, it's going to prompt me, do I want to save? In which case I'll just type Y for yes. And then it's going to ask me, where do I want to name, or what file do I want to name it? I'm just going to keep draft.txt, so I'll just hit enter, and then I'm out. You could also, if I just press up and I do run the command again, you can do, I think, control and O, which will ask you, again, do you want to save? And you hit enter, and so that saves, and then you can do Control X, and now it won't prompt you to save on exit. So I went through that pretty quickly. The shorthand, the keyboard shortcuts are in the teaching notes. So I encourage you to take a look at those if you're still stuck inside of Nano. There's a question in the chat. So why do we sometimes get subdirectories of files like bin.git, et cetera, et cetera? Well, it depends on where you are. So like if you're listing the contents of your home directory, then you might have all of those files that are there. And so then I guess I don't understand the question. So why do we sometimes get subdirectories files like bin.git when you create a new directory? Well, if you're creating a new directory, you shouldn't be seeing any other directories besides the one that you created. I'm not sure I understand the question. I'll keep an eye on the chat to see if that comes back. Okay, so we created a directory and we just created a file. So now if we run ls-f again, so here's our file, draft.txt. And if we did ls-lf, then you will see, so here's this -l command is a little bit, gives you a little bit more information like we saw before. And so now our timestamp, so this clearly isn't local time. This is, I don't know what time zone that is, some North American time zone, I guess. And then the name of the file, and then the permissions over here. Okay. So Nano is a really simple text editor. You can use it to create any kind of text file. That is like, it's just creating a regular text file. So if I did something like nano if I did nano train.py and hit enter, then I could type some import import numpy as np and import pandas as pd, print hello world, something like this, and then I was to save that. Now I've typed something that is valid Python syntax, I think, and then if I ran that with the Python program, it would import those libraries and run whatever code is there. But it's only for text. So you can write whatever kind of text you want in there. It can be valid Python or valid Fortran or valid whatever, but you can't use Nano to like make a binary file like a GIF or a JPEG or something like that. So Nano, so there are other text editors like Emacs or Vim, which are really heavy-duty text editors that are terminal-based text editors. Nano is good for doing simple things like making minor edits to scripts and things like that. I use it for really light touch editing of things on iBex. I'll use Nano just because it's simple in there. But in general, if you want to do serious kind of text or terminal-based development, then you might want to look at Emacs or Vim. Right. Okay. So I guess this is a good time to talk about this discussion about, you know, what kind of files can Nano create, about what's in a name. So this is in the, so here's some links to some different text editors. You know, there's links to Emacs, Vim. Jupyter Lab has its own built-in text editor. My personal favorite is Microsoft Visual Studio Code, which can be run as a server on a remote workstation. So actually you can run Microsoft Visual Studio Code on ibex and have it run in your browser. If you want to do, that's how I would do serious software development on ibex. But that's outside the scope of this course today. So let's look at, so what's in a name? So file extensions are basically conventions used to indicate to a human what is the contents of a file. But from the computer's perspective, all files contained are just bytes. So when you pass a file into a program, the program will understand how to convert bytes into something useful based on what the developer of the program wrote when they were developing the program. But so if you have a program that's written to consume text files, then if you pass it in a PDF, it's not going to work. But if you pass it in a text file, it will understand how to convert the bytes that are in that file into something useful. But file extensions are just human conventions. Changing the file extension does not fundamentally change the file and the bytes in the file in any way. So, if you have a picture of a whale, the example here is like a really, perhaps a bit of a silly one. It's like, if you have a picture of a whale, but you change the file extension from PNG to MP3, it's not going to, convert the bytes in that file from an image into a recording or an audio file. There's a question in the chat about how to save what we did in the file. So the way that you saved, and I went through it quite quickly, but it's covered in the lecture notes here, actually, in this call-out box with control. So when you typed your information into Nano, then when we exited the file using Control X, it asked us, did we want to save? And we said yes, hit enter, and then we had the name of a file and we hit enter. Or you can do it this way, which is the Control O for write out, which basically writes the file or writes the buffer to disk, and then you can exit. So let's do this. I'll do this again. So I will open, I'll do something. And I will do print. So now I'm just going to put something else in here. 2 + 2. And so now I can do Control and O. So that's going to write the contents of the buffer, which is basically everything that you see here on the screen, out to a file. And it tells you at the bottom, file name to write. And it provides you as a default the current file name, which is train.py. So I'll just hit enter. And now see at the bottom, it says it wrote 6 lines. So it wrote 1, 2, 3, 4, 5, 6 lines from the buffer out to a file. And now if I hit Control X, I can exit. And then of course I could rerun this Python script again. Okay. So moving files and directories. So this is actually moving and renaming files and directories. So let's go back here. So in this section, we're going to cover basically moving and renaming files and directories, and then copying files and directories, and then removing files and directories. And then once we get to the end of that, we'll take a break. Right, okay, so moving files and directories. So we want to go back to our data, our data directory. So that's the parent of the current directory. So let's go one level up, cd dot dot. We can do pwd, see where we are. Okay, so our draft.txt, we basically want to rename that file from draft.txt to quotes.txt, which is a more accurate reflection of the contents. So we'll use the move command to do this. So we do move space, and then the first argument is the file that we want to move, which is thesis drafts, followed by a space, and then the second argument is where we want to move it. And this is where kind of moving and renaming can be used to do the same thing. So if we want to move it to thesis quotes.txt and hit enter, now if we list the contents of the thesis directory, we'll see that there's no longer a draft.txt. Now we have a quotes.txt. Now, so here's our first kind of danger zone type or warning for using a command. So with move, you have to be careful, because if you could silently overwrite or accidentally overwrite an existing file. So if you run, move a file to a file that already exists, move will silently overwrite the existing file, and this could be dangerous. If you're not careful, if you accidentally moved, some little file to a thesis/draft.txt, you might accidentally overwrite your whole thesis with one command. So the way that you can get around that is by using this -i or -- interactive, which will make bash automatically prompt you. Let me see if I can come up with a demo of this. So I will use a command called touch, which is another way to create a file, important file. Okay, so that touch command just created, whoops, it's getting a bit messy. So if I do ls thesis, okay, so that touch just created, without opening it or anything, just created a file with a particular name. So if I was to do the following, move thesis quotes.txt to thesis important file.txt. So this would silently overwrite the important file with whatever the contents of the quotes.txt file was. If I wanted to guard against that, I could pass the -i option, or the long form of that option, which is -- interactive. And then I'll be prompted, do I want to overwrite this file that already exists? And I'll say, no, that file is important. So I'll just type N for no and hit enter. And then nothing will have happened. If I do ls-f again, ls-f thesis, so nothing happened, basically. So that -i flag is a guard to protect yourself, and we'll see it again when we talk about removing files. Okay, let's do something else. So if we wanted to move this quotes.txt file to the current working directory, Remember, the single dot is a reference for the current working directory. So if we pass this in, now this quotes.txt file has been moved to the current directory. And if we were to look at ls-f of the thesis directory, now it's gone. So we basically moved it from the current directory, or from its directory to the current working directory. And if we wanted to move it back, of course, we could do move quotes.txt to thesis. And then if we do, and now it's back. So there's a question, can I do move python.txt to python.py? So you could, you could do that, but remember that the contents of a file are what the computer actually kind of parses and understands based on the program that you pass the file into. So if you have a python.txt that, you know, just as an example, so if I did make dir I'll just make dir source for source code, and then if I cd into source code, and I did like let's see, nano python.txt, just as an example. Okay, and I put ha. This is actually just a normal text file. It is not a Python script. And then I do Control X, save, yes, enter. Now, so there's my python.txt. I could move python.txt to python.py. And now if I try to run that python.py file with Python program, of course it gives me an error because the bytes that are in that file do not make sense to Python. Python only knows how to interpret bytes that are written in the Python language. Does that make sense? So yes, you can move, basically it's yes, you can use the move command to rename the file, but just renaming the file and changing the extension doesn't automatically mean that the contents of the file will be useful in any way. Okay. Okay. So I think what I'm going to do is I'm going to skip over these exercises and just let you kind of go over them over the break that we're going to take. And then if you have questions, and we can talk about them later. So Kieran said he just meant to ask about changing the extension because sometimes this doesn't work in Windows GUI. So yes, of course, you can use the move command to change the extension. And you're right. So sometimes, because GUIs will often make, in an effort to be more user-friendly, they will make assumptions about what you want to do in terms of file extensions and things like that. And sometimes they actually make it more difficult than it ought to be to do something simple like change an extension. But here with the terminal, you have complete control. You can use these commands to do just about anything that you need. But of course, you know, with that control comes some responsibility. Okay, so copying files. So we talked about moving, but what if we just want to copy a file? So let's go back over here. So we have our, where am I? So I am in the source directory. I want to go back right here. Okay. And just to keep with the notes, I'm going to move the thesis quotes to the current directory. Okay. So what if I want to copy this quotes? I'm going to clear now. If I want to copy this quotes.txt file back to the thesis directory, so I can do copy. So CP is the shorthand for copy. And then the name of the file that I want to copy. And then the last argument, or the last argument is the directory into which I would like to copy the file. Thesis. And if I want to rename and copy at the same time, I can actually pass the name of a file as the destination. So here, the first argument to the CP command is the name of the file to copy. The second, or the last argument, better to think of it as the last argument, is a path to a directory where you want to copy the file, or the path to the file name where you want to copy the contents of the file under a new name. That makes sense. So now if you hit enter, and then if you run ls ls thesis, you'll see there's that quotations dot text. Okay, so we can also copy, so copy only works on a single file. So if you want to copy the contents of a whole directory, you need to copy a directory recursively. So that is basically go into the directory and continue to copy every file in that directory until you're done copying files. And to do that, we pass the -r. And then if we want to copy the whole thesis directory to another directory called thesis backup, maybe, then we can do that. And now if we do an ls-f, so here's our original thesis directory and the original thesis backup directory. And then we could do ls, and we could list what is in thesis. And now actually you can pass in what's called a list of arguments to be passed to list one at a time. So we could do this. And this is going to first it's going to print the contents of the thesis directory and then the contents of the thesis backup directory, just so that you can see that they're the same. So that's quite useful. So that copy command is what is used to copy files or directories from one location to another within the same file system. Now, if you're working on Ibex and Shaheen and you need to copy files from your laptop or workstation to those remote machines, or from those machines to your laptop or workstation, then copy won't work for that. But there's another tool called Secure Copy, or SCP, and some other tools for doing that. And those type of tools will be covered in the like Ibex 101 or the Shaheen 101 training, which is happening very soon. I think has already been announced. So be sure to go to those trainings if you want to learn how to build on top of these basic shell commands to kind of move things back and forth between remote servers. Okay. All right, so now I'm going to do removing files and directories. So we're going to skip ahead a little bit over these exercises that you can come back to. So removing files and directories. Okay, so let's take a look at what we have here. So we have this quotes.txt file, and we'd like to remove it. So we're going to run the rm command and --help. So we can take a look at what the options are. So for the rm command, which removes files. And I'll come back to it. Says remove actually unlink the file, and I'll come back to what that means in a minute. But there are some options here. The important one, I guess, is the -I. So this is that same guard that existed with the move command to prevent you from overwriting accidentally. So the -I here will prevent you from accidentally removing files. It will always ask you, do you really want to remove this? And you say yes or no. And there are some other options in here. So the -R for recursive to remove the contents of the directory and remove the directory. So there's a question in the chat, topic, is Shaheen 101 course the same for IBEX as well? I think they're two different courses. There might be somebody from KSL who is hanging around on this training. If so, maybe they can respond and confirm. But I think they're two different trainings because those are two different systems. So some of the stuff is the same, but the Shaheen has a lot of Shaheen-specific things that are relevant. So I wouldn't. If you're comfortable using IBEX, that will give you certainly a leg up over someone who hasn't used any remote computing system before. But I would still go along to the Shaheen 101 training because I suspect that there are significant Shaheen-specific content that's relevant. Okay, back to removing files. So let's clear this out. So if we want to remove our quotes.txt file, we can just do rm quotes.txt. And now our quotes.txt is gone. Now, what actually happens with remove is that there's a couple of things that are worth noting about remove. So first is that there is no notion really of like a trash can or a garbage bin. Like when you remove something, you should assume that it's gone forever and not recoverable. Now, that's not entirely true, because what remove actually does is it unlinks the memory where the contents of that file are stored, and basically says that that memory is now free to be used by the operating system for other things. The operating system might immediately run some kind of garbage collection routine to erase the actual contents of the memory, in which case it's gone. But what might actually happen is that the contents of that file are actually still there on the memory and they haven't actually been collected yet. It's just that the memory has been unlinked and marked for, say, garbage collection in some sense. If you're a CSI computer forensic scientist or something like that and know how to use those tools, you might be able to dig in and find bits and pieces of data remaining from files that had been RM removed. But that's well beyond the scope of this course. For your purposes, you should assume that if you run RM on a file, that file is gone and not recoverable unless you had backed up snapshots in that particular directory or something like that. So removing is forever. Okay, so what if we did something like this? So remove thesis. So we'll get an error. So cannot remove thesis. So because thesis is a directory. So the remove command only works on files. And this is, in some sense, this is kind of a built-in guard, because deleting a file can be important. But deleting a directory might be even more catastrophic if it's the wrong directory. So the remove command will automatically fail if you try to apply it directly on a directory without passing an additional option or things like that. Right, okay, so if we want to remove the directory, we have to pass the R flag to recursively remove the files in the directory and then remove the directory. So now the thesis directory is gone. So it's a good thing that we had a backup, because now that directory is gone and unrecoverable. So we could do something like this. If we wanted to practice our move command, we could move, or actually maybe a better thing to do would be to copy our thesis backup to a directory called thesis. And remember, because we're copying a directory, we have to use the -R. And now we've got our thesis directory back. So there you go. So if you take nothing else away from today, you will have learned the importance of backing up and the sequence of bash commands that you can use to recover a directory of data that you accidentally deleted but had backed up. So in the chat, can we use chmod + x commands to make the file executable like we do before .sh? So Rakesh, that's a question about permissions. So I'm not going to cover permissions today. That's a little bit too far afield. The short answer is that I typically do not directly execute my Python scripts, but rather pass the Python script to the to Python manually, because that way I know exactly which Python is being used to execute my script. But I don't want to go any further off topic than that. Okay. Okay, so the last thing I'm going to cover before we take a break is, so for the most part, we've been working with single files at a time, but you can actually work with multiple files. Most of these commands will take a space-separated list of arguments of files as an input, and then we'll operate on all those files one after the other. So for example, you can copy two files like this amino acids.txt and animals.txt to a directory called backup in one line, which will copy both of these files into that directory. And what's really powerful is that you can use wildcards to pattern match on files. So this is really useful if you have a structured format for naming your files, then you can make them amenable to pattern matching and use of wildcards. So you could use something like a star.pdb to create a list of all files, and it could be like 10 files or 10 million files that match that pattern, that end in that particular extension. And then you could pass that into a program that processes files with that extension type. And so this pattern matching becomes super powerful. And we're going to see some examples of that in further episodes. So I'm going to kind of skip over these exercises and leave them for you to kind of go over on your own. All right, so we're going to wrap up, and then we're going to take like a 10-minute break, and then I'll come back and then we'll start up. Again. So the key commands that we covered were copy, make dir, move, and remove. So copying is for copying the file. Make dir is creating a new directory. Move moves or renames directories or files. And remove removes a file. And then I went very quickly over the pattern matching things, but we're going to see some more examples of that. Okay. So at this point, we've covered, we've covered kind of navigating, basic commands for moving around the file system, basic commands for creating directories and files and copying things and deleting things and whatnot. And that is, in terms of like the day-to-day things that you would need to do when you're on working with Bash. Like most of the things are going to involve these kinds of commands. So we've actually given you in just these kind of probably less than 10 commands, the power to do quite a lot of your day-to-day business directly from the terminal. Okay, so one question via chat before we break: can we use wildcards for directories as well? And the answer is, I believe so. So if we were to do ls thesis star, yeah, so there we go. So that ls thesis star basically ran the ls command on anything that matched this pattern, which was basically the thesis directory, the thesis-2 directory, which didn't have anything in it, and then the thesis backup. So yes, you can use wildcards for pattern matching on directories. Okay, cool. So for the moment, I'm just going to stop sharing, and then I'll turn my video off. So we'll take a 10-minute break. I'll set my timer, and then we'll come back and pick up where we left off. All right, see you guys in 10 minutes. Okay, so that was 10 minutes gone, so we're back. So there's a question about somebody saying that they were having some connection issues. So audio, okay. So was my audio clear for most everybody? So can I just get a check yes if my audio was clear and no if no? In the participant section of Zoom, just so I can try to get a sense of if this was a more consistent issue or if it was a sporadic. Okay. Okay, well, I will try to take note of that for next time. I think I'm working on a wireless connection now. I'll try to make sure that next time I'm on a LAN connection, hard connection. Okay, cool. So let's see, where did we leave off? So we were done working with files and directories. Pipes and filters. This is my favorite episode. Okay, so we've covered the basics. So now with pipes and filters, we want to see how we can combine these basic ideas, these basic commands that we've learned to do new and interesting things. In particular, we're going to see how to redirect output to a file, which is really useful. Most of the time, we don't really want the output of our commands to just come back to the terminal window or the terminal screen. We want to see how to construct command pipelines with 2 or more stages, and talk about what happens in a program or a pipeline if there's not any input provided for processing. And then we're going to talk a little bit about Unix philosophy of small pieces loosely joined, which is a very powerful way to think about computing. Okay, so now I'm going to go back to sharing screen. Okay, and so I'm going to hop over to Jupyter Lab, and I'll just refer to the teaching notes. So first off, let's clear out this madness and go back to teaching notes. Okay, so we want to look at this molecules directory. So let's look at molecules. Okay, so in this molecules directory, we have these special text files, .pdb files. So we're going to do some processing with these with these files. So first, let's cd into the molecules directory, and so we're going to use this command wc. Take a look at what it is, and we can kind of read through here, and we'll see that it's for counting words, characters, bytes, and lines in a file. So it's basically performing a word count program on a file or files that we pass in. So let's see what happens if we pass in a single file. So if we do ls-f Cubane. So let's do word count on Cubane. And so what we get back is the output, which is the number of lines, followed by the number of words, followed by the number of characters in the Cubane .pdb file. Okay, interesting. Maybe we can do something else with this. So I'm going to do clear. So what if we do word count of star.pdb? And here's our first example of this powerful wildcard pattern matching technique. So here we've applied this word count program to all the files that match that pattern. So this might be, in this case, it's like 6 files. But if it was 6 million or 10 million, the command would be the same, and it would process all of those files. Obviously not as fast as it takes to process 6 files, but it would process all the files with the same command. So this is a pattern that if you have some files that you need to process with a program and the files have a common extension, you can do the name of the program followed by star dot whatever your file extension is, and that's the same as if you kind of manually passed in each of those files to the program. And then you'll get the results back in the terminal, and we'll see in a minute how to redirect these results to a file instead. So let's try to maybe motivate this a little bit more, more specifically. So what if we wanted, instead of like the number of lines, words, and characters, what if we wanted to look at only the number of lines in a file? Maybe these .pdb files, the number of lines in a file tells us something about, tells us something useful about the file itself. So we can pass in the -L option. So if we go and look at the help menu, the -L option will give you the number of lines in PDB file. And so there, that's basically just selecting off this first column here. Okay, so that's a little bit. And if we wanted the number of words, then we can pass in -W, and then for characters, it's -M for some reason. Okay, so now, let's suppose that we wanted to find the file that has the fewest number of lines. And here we can look at, so we can look at the output of our word count star.pdb command and just glance at it and say, well, the answer is clearly this file, methane, which has 9 lines. But suppose that you had 10 million files and you needed to find the file with the smallest number of lines. How would you do that? Obviously, looking through them is not going to be very effective. So how can we do that? Well, the first thing we could do is just select out the number of lines from all these PDB files. And then instead of returning that output to the terminal, we can redirect it to a file using this greater than sign. You can think of it not as a greater than sign, but more as like an arrow saying redirect the output of this command to this file, and we'll call this lengths.txt. So now I'm just going to clear this out again. If we run ls, we'll see we've got these PDB files, but then we also have this lengths.txt file here. Okay, so now we want to look at this file. So there is another command called cat, which is actually short for concatenate, that allows us to look at the contents of a file. So cat and then lengths.txt basically returns the contents of the file and puts it into the terminal. So here we can see that this is the same output that we got from running the word count command in the terminal. But we redirected it to a file using the arrow, using the greater than symbol. Okay. Now, there's an exercise here which I'm just going to kind of walk you through, and then we'll pick up with, because it's important for the next part. So if we have the sort command and we run it on this file, the output is the following. But if we run sort with the -n on the output, we get maybe what you would expect, which is the numerical sorting. So sort by default is going to compare everything as strings. It's basically going to compare, it's going to compare first each character in the string, and if it's the same, it goes to the next one. Otherwise, it uses the ordering based on the first character. So we're going to use sort in a minute to solve a problem. Okay, so in the chat, there's a couple of questions. So does this also work for, let's say, sbatch star.sh on IBEX? So that is actually a good question, and I don't know. I've never tried it. I want to say, well, gosh, the short answer is I don't know. And I'm not logged into IBEX now, so I can't check the help command of the help menu of sbatch to actually look and see. I would encourage you, if you come along to the IBEX or Shaheen training, you should ask that question. And then there was another question of how to know the number of files in a directory. Remind me to answer that question in about 10 minutes. I need to cover a couple of other things first, and then I'll show you how to answer that question. Okay. So I just mentioned a little bit about the sort command. So the sort command, sort with the -n, will sort the contents of a file numerically. So now if we pass in this lengths.txt, the output that we get is the contents of the file sorted numerically on the contents of the first column, basically. So now we have from smallest to largest. So now we've got our answer here at the top. So we could, run the previous command and pipe the output to another file, maybe called sortedlengths.txt, and then we could cat that file to see that it contains the same answer. Now there's another command called head, which takes as its argument a number of lines and then returns that number of lines from a text file. And so there's our answer. Right. And if we needed the list of files, the 3 shortest files by lines, we could do that, and we'd get 3. Now, this is all kind of quite convoluted. I mean, we ended up creating 2 files. Like, isn't there a better way to do that? And the short answer is yes. We're going to see the pipe command in a minute, so that we can do all of these steps kind of one after the other in one command and avoid having to create all these intermediate files. But before we get to that, I want to mention a couple of things about output redirection. So redirecting to the same file. So this is a bad idea. And it's bad for the reasons that you might think it's bad. It's like here we're trying to sort the contents of this file, but then also at the same time rewriting the contents of the same file. Like, that seems like it's going to create garbage, and it's a bad idea. And it is in fact a bad idea. So don't do that. There's a nice exercise here about the difference between a single greater than and a similar operator, which is greater than. And basically, the first greater than is basically redirecting output to a file, and it will overwrite the contents of the file. Greater than operator redirects output to a file and appends that output to the existing contents of the file. So it's basically the difference between redirect and overwrite, which is the greater than symbol, and redirect and append, which is the double greater than symbol. That distinction is important because this output redirection is really powerful, and it's what allows you to basically automate a lot of analysis and collect the results in a single file, basically. Okay. So, now let's talk about this pipe character. So that kind of toy problem about basically you've got a bunch of files and you want to find out what's the shortest file by number of lines. We went through and showed you how to solve that, but it was a bit convoluted and confusing, to be honest, and I think we can do better. So the first thing we're going to do is we're going to institute, we're going to talk about the pipe character. So sort, so let's look at the last kind of command that we ran, which was to sort numerically our lengths.txt file. So instead of redirecting that output to a file just to be read in again as the input to another command, can't we just pipe that output to the input of another command? And the answer is yes. And this pipe, so this is the first example we've had of a pipeline. This would be a two-stage pipeline where we have taken some data files or files in, passed them into a program to generate some intermediate results, which we then piped as the input to another program. And here, these programs are kind of simple programs. It's sorting and taking the top n lines basically of a file. But the same kind of approach could allow you to chain together, these could be inputs to some bioinformatics pipeline, and this could be some bioinformatics algorithm that takes quite a long time to run on maybe millions of input files. But then once those million input files are generated, they then need to be processed by another program, and you could just pipe the results to this other program. So it's this pipelining that I'm giving you this kind of toy example here, but I want you to really kind of try to internalize this way of working, because we can write these pipelines at the command line, but you can also roll them up into job scripts and submit them via, again, IBEX or Shaheen or a public cloud, or you could just run your bash scripts on your workstation or laptop. But we can even do better, because actually this lengths.txt was itself an output of another process. So if we delete this and go back even one level, and remember that lengths.txt was itself the output of word count of all these raw input files. So there's a three-stage pipeline that starts with raw input data, these .pdb files, and then performs three stages of a pipeline, one after the other after the other. And there's a nice graphic here about this concept of pipelines. So you should think of these little commands as like little Lego bricks. And the Lego bricks are meant to be kind of joined together to create more complex shapes and patterns and outputs. And it's the same with these Unix shell commands. Each of them is like a little Lego brick, and you can chain them together using this pipe character to create ever more complicated and sophisticated analysis pipelines. And just like Lego bricks, only certain kinds of Lego bricks can fit together with one another. Only certain kinds of commands can chain together with one another, and what kinds of commands can be chained together to form these pipelines with one another depends on kind of what is the input and the output like, or what is, with the Lego analogy, it's like what is the, you know, the little nub pattern on one Lego brick, and how can it fit into like the input side of another Lego brick? You know, it's like the inputs and the outputs. So in our previous example, you know, the expected inputs to the word count command was a list of files. And the expected, and it generated, you know, a file, single file as an output. The expected input of the sort command was a single file, and it generated a single file as an output. And the expected input of the head command was a list of files, or a single file. And so you can see how the inputs and outputs are the same kind of type, in a sense. And so you can chain them together, and then they work well. Right. All right, so because this pipeline idea is so important, I want to take 5 minutes and have a go at these exercises. So this one is a reading comprehension, and talks about, introduces another command, tail, and then pipe construction introduces yet another command, cut, and unique. So 2 more commands. So I'll set the timer for 5 minutes. So please take a look at these exercises, and then we'll come back and I'll pick 1 or 2 of them, and we'll work through them together as a group. And in the meantime, if there are any questions, you know, just pop them in the chat, and I will do my best to kind of answer them. So there's a question in chat about how can we access a remote workstation by terminal. So that is, that's going to be covered in either IBEX 101 or Shaheen 101, depending on which of those machines you need to access, or you can go to both. It uses a tool called SSH, which is a secure shell, but it's outside the scope of this particular course, which is to try to cover the basics of what you need to know to operate inside the terminal. And then IBEX 101 and Shaheen 101 could then cover the mechanics of actually accessing the terminal via SSH from your laptop or your workstation, and then issues related to moving things back and forward across the network. I do have some materials that cover some of that information, and I will make those available. I'll share the links basically to those materials when we're done today. So if you want to go through those, you can kind of maybe get a little bit of a head start on some of the stuff that you're going to encounter in the IBEX 101 and Shaheen training when it happens. In fact, since I'm just sitting about, I will grab that link now and share it in the chat. So the Shell Extras course covers a good bit of stuff that you're going to find in the IBEX 101 and the Shaheen 101, but those courses focus specifically on IBEX and Shaheen. This is going to be more general, but it will cover things like how to work remotely, how to connect to remote computers using SSH, and how to copy things back and forth using this SCP protocol, how to transfer files from the internet and download them to remote servers, permissions, which I mentioned today, but it's outside the scope of the course, shell variables, profile customization. So this is all like more advanced stuff that's like nice to have, but is kind of a little bit outside the scope of the time frame that we have to cover this afternoon. Okay, so that's my 5 minutes timer gone. So let's take a look at some of these pipeline questions. So let's start with pipe reading comprehension. So we're told to look at this file in the this animals.txt file. So we need to go up one level, and then maybe into this. Where is this file? There it is, animals.txt. So let's go into data. And let's run cat on animals.txt. All right, so that's the file that we're working with. And the question is basically what comes out, what is the contents of this final .txt file that's referenced in the exercise? So it wants you to understand kind of what's happening as the data flows through this pipeline. So the way we can start is by just kind of looking at this pipeline one stage at a time. So cat animals is the first step in the pipeline. So that just basically generates output. So if we were to pipe that output to the head command, this is going to select off the first 5 rows in that file. Okay. If we were to then pipe that output to the tail command, what has happened here? So we've not seen the tail command before, but if head selects the first n rows, tail you would think would select the last n rows. Okay. So then we take the first 5 rows of animals.txt, and from that we then select the tail, the last 3 rows. So that's these 3 rows here. And so that's why we get that particular output. Now, if we then pipe that to sort R, what has that done? So it has taken these 3 files and sorted them in reverse order, comparing characters. So all of these are the same until you get to the days, and then you have 6 and 5. But the zeros match all the way down. So then you compare the 6s and the 5s. So these 6s match, and then the commas are the same, but then R comes after D. So there's the difference. And so that's why this first character, or this first line, rabbit comes before deer, and then raccoon comes last because raccoon has an earlier date. Okay. Okay. Let's look at. Well, actually, I'll leave the solutions to these as exercises for you, because I want to keep moving. Cover some more material. Okay, so let's try to give so we gave a toy example. So now let's try to give an example that is supposed to be more emblematic of the type of thing that that you might use these tools for in your own research. Okay, so clear, and let's go up one. Okay. So Nell has this data, or no, it's not in there. It's, there we go. So she has this, these files that were generated from her physical samples. And so the first thing that Nell wants to do, so this is like, imagine that basically you are now have received all of these data files that were spit out by some analysis machine based on some raw lab samples or something like that. And now you want to do some like sanity checking on these data files to make sure that it seems like the analysis, the machine that you pass the physical samples into has not generated garbage. Like you just kind of want to do some sanity checking to make sure that you've not got garbage, because garbage in, garbage out. So and so the first thing we're going to do is we're going to count the lines in the text file. Okay. What? Where am I? I am not in the right data. I'm not in the right folder. I need to change into the North Pacific Gyre. Now, if I run the word count program, okay. Now, the motivation behind this particular command might be because, Nell, as an experienced scientist that has worked with these kinds of files before, knows that if the file has been properly completed and full analysis has gone through without issue, then the file ought to have exactly 300 lines in the file. That means that's just kind of a sanity check to note that it has been properly sequenced or whatever it's doing. And so we could do, we can quickly glance at this and see, well, maybe you will have spotted that one of these files is a bit shorter than the other. But if you had 10 million files or something like that, you would definitely not have seen that. So, but we could solve this again with pipelines. So we could pipe the output of this word count to sort numerically, and then look at the head, the first 5 lines. So there we see, there's that one, it immediately rises to the top. We can see that there's one file that's shorter than the other. We could also check to see if there are any files that were too long by running tail. So here, if there was a file that had like 301 lines, then we would know that it should show up at the bottom, but there I'll show up as 300. So okay, so there we've done some sanity checking. Okay, but we might notice something else. So looks like all of these either end in a B or an A, but then there's this file here that ends in a Z. Well, what does that mean? Again, if you are, again, the idea is that these are kind of structured output files from some machine that you're used to working with, and that these file naming conventions are meaningful. So, B and A might have, particular codes, and Z has some other code. So Z might be an indicator that means that there's missing information in this file. It's like it's missing some important information, and Z is used to indicate that. So then you could say, well, how many files have missing information? Well, you could do an ls files that match this pattern, star.txt. And you'll see that, oh, there's 2 files that actually match that pattern. So it looks like there might be 2 files that have missing information or are corrupt in some sense. So maybe we want to exclude those files from analysis. So then this becomes another pattern matching problem. We don't want to necessarily delete these files, even though they might be kind of have missing information. Like, deleting them doesn't seem to be the right thing, but we want to ignore them in further downstream analysis. So we can use another pattern matching. So I'm going to clear this out. So if we wanted to list all files that have ended extension PDB, but whose character just before the period is either A or B, we can use this. And you can you could have a whole course on wildcard, regular expressions, and pattern matching. This is something that if you're doing genomics or bioinformatics, you're probably much more expert at than I am, because a lot of genomics and bioinformatics is pattern matching on DNA sequences or something like that. So here, if we run this, so notice that I've got the whole, so what happened here? So the error that I got cannot access this. So basically this matches no pattern. And why is that? Wrong file extension. There we go. So then that returns all of the files in the directory that match that pattern. Okay. So let's go back here and take a look at so let's talk through the removing unneeded files, and then I'll leave the wildcard expressions as an exercise for you guys to go over later. So suppose that you have, you actually do want to delete some processed data files and keep only the raw files and the processing script in order to save storage. So this is quite common. So particularly if you have an analysis pipeline that takes only order of hours or something like that to rerun, maybe you don't want to save all the intermediate inputs. You just want to have your raw data plus a script that generates the processed or like the final data that you need, and you don't want to save any kind of intermediate inputs or something. So if the raw files end in .dat and the process files end in .txt, then which of the following would remove all the processed data files and only the processed data files? Anybody want to take a guess? You can just chuck an answer, start chucking answers into the chat, I guess. So I see second. Anyone else? What do you think the third one would do? Remember that that bash is space sensitive. So what do you think the third one might do? Rakesh, exactly, clear all. Yeah, so it would be remove star, and it would be you're passing basically any files that match the pattern star, which is of course every file. And so then it would remove all those files. And then it would say, well, is there a file with a .txt called .txt? And actually there isn't, so it wouldn't remove that file. It would probably throw an error. But so that's an example of how you should be careful when what you're typing when you're using the remove command, because this accidentally putting a space between star and .txt is the difference between doing actually what you wanted to do and catastrophe. Because this remove star space.txt would remove all of your raw data files and all of your processed files and all of your scripts, which would be very bad if you didn't have backups. And similarly, star.star would match any file with any extension, so that would also be quite potentially catastrophic. Okay, so we actually covered quite a lot in this pipes and filters episodes. We talked about several new commands. We saw cat for displaying contents of a file, head and tail, which is used to extract the first, by default, 10 lines of input or the last 10 lines of input from a file, sort for sorting, word count, which does lines, words, and characters and inputs. And then we saw how to redirect output and overwrite, which is the single greater than operator. And we saw how to redirect output and append, which is the double greater than operator. And then probably one of the most important things is this concept of the pipe character, or the pipe operator, which allows you to build up these pipelines that pass the outputs of the previous stage of the pipeline as inputs into the following stage of the pipeline. And we talked about how to think about each of these stages of the pipeline as kind of Lego bricks that you can combine and build more complicated bits of analysis. Okay. Any questions? Anybody want to chuck something into chat to talk about before we move on? Sorry, Rakesh, I didn't mean to smile when I read your comment. That I can imagine that would lead to some sleepless nights. And this is something that will be covered in IBEX and Shaheen 101. They will cover kind of which file systems are backed up and which file systems are not backed up. And the reasons why, like for example, your Scratch directory, which will be the file system where you store most of your data for analysis, that's not backed up. There are reasons for that. And they'll talk about that, and they'll talk about your home directory and how your home directory is backed up and things like that. So they may even talk about Datawaha, which is the archival data storage solution provided by our colleagues at the Research Computing IT. But I'm not entirely sure about that. Okay. So let's move along. Loops. Okay. So let's see what else. Loops and shell scripts. Okay. So my hope is to cover in the last 40-ish minutes that we have to cover loops and shell scripts. Like I want to at least talk through both of these. But then I'll leave the rest of the lecture materials for you to cover on your own. All right, so let's talk about loops. So the question is, how can I perform the same action on many different files? So we've actually already seen one answer to this question, which is the use of these sync commands and wildcard pattern matching. So if you have a command that takes a list of files as an input, then that's kind of like a for loop in the sense that that command is going to process each of those files one after the other as if you were just looping over the files one at a time. So it's kind of like a for loop already. But here we're going to talk about, we're going to give some examples of explicit for loops. And you'll see kind of in these examples why you couldn't, in some cases, use a pipe operator directly. So we're going to write a loop that applies to one or more commands separately and each set of files. Talk a little bit about loop execution so that you understand kind of the different parts of the loop. Kind of preview of coming attractions. Like if you've programmed in any programming language, Python, R, Julia, C, C++, Fortran, like the general concept of a loop is basically the same, and it's the same here. The syntax is obviously going to be different because Bash is a different language, but conceptually it's going to be the same idea. So if you understand the concept of a for loop from somewhere else, then it's not going to be any different here. It's just a different syntax. So we're going to walk through all that stuff. Okay. So loops are going to be how you're going to repeat a command or set of commands for each item in a list. And that makes them, probably one of the most powerful tools that you will require, that you'll encounter. And what makes Bash loops more potentially or more useful is, it allows you to have a loop that can apply a bunch of different programs to kind of the same input, or to a collection of input files. So, obviously you can write a loop in Python, and you can, in your Python script, you can use a for loop in Python to loop over a bunch of input and do some analysis in Python. But what if you have a Python program that takes a whole bunch of raw input files and then outputs some other file, which then is read in by, which is then taken as an input to some other analysis program that might be written in Fortran, and then that generates yet another output file, which then needs to be processed by some visualization package that's written in C. So but you need to do basically the same kind of steps of analysis. You need to run the input file into this Python pre-processing program to get an output file, which you run into this Fortran analysis routine, which gets another output file, which you pass into this visualization program to generate a plot. And you need to do that 1,000,000 times or something like that. Then you can write, after this episode, you will understand conceptually how to write a Bash loop to automate that process, to basically take the input file, feed it into the Python program, get that output file, feed it into the Fortran program, get that output file, feed it into the visualization program written in C, and get your plot. That's the basic idea. But of course, we're going to start with a toy program. So let's suppose that we have a whole bunch of these genome data files that have this kind of format: basilisk.dat, minotaur.dat, unicorn.dat. And they're actually in, I'm going to switch back to my Jupyter Lab instance again. And they're actually in this creatures directory. So I think I need to go up 2 levels. Yeah, creatures. All right, so I've got a couple of these .dat files in there. Obviously, there might be many of these files, like thousands or something like that. But here we've only got 2 for simple purposes. So if we run the head command to look at the first 5 lines of all of these .dat files. So here we can see that we've got some kind of like header here. So we've got common name, classification, and then some kind of date, and then a bunch of C's, A's, G's, and T's. So this looks like some kind of DNA sequence or something like that. Okay. Now, what we want is actually we need to process these files, but the data that needs to get fed into the next stage in the pipeline is actually only these C's, A's, G's, and T's data. This part we basically need to cut out. before we pass it into, so this is like a simple pre-processing operation. It's like we need to cut out some rows from our raw input data before we can feed it into whatever analysis routine we need to use. So we could do this manually by doing head. So if we take well, before we get to that, let's do something simpler. So let's suppose that we wanted to extract the classification for each species. So that's basically the second row. So if we did head to dat, and then piped that into the tail to pull out the last one, then we get something that doesn't quite work. So that doesn't work. So like it seems like we could do this with this pipeline, but it actually doesn't quite work the way that we might expect, because the output of the first command is actually this text here. And then if we pluck out the last line from that text, we only get this one line. Instead, we want this and this. So this is, again, it's a toy example, but it's an example of where we need a for loop. Okay. So here I'm going to hand roll a for loop, and it's going to be a bit tedious, and then we will I'll show you how to do this in a text editor. So we can do for file name. So the file name is going to be what's called the looping variable in a list of file names. And here we can pass in either a space-separated list of files, or we could just put star.dat to have Bash expand that out for us. And then we'll hit enter. Now notice that now my prompt has changed. So instead of the normal, where is it, $ prompt, I have this this greater than symbol prompt. So that means basically I'm kind of in a sub prompt for this for loop that I'm writing. Do, and then I'll add some white space, which just kind of makes it a little easier to read. So I'll just do 1, 2, 3, 4. The number of white spaces is not important. It's not like Python where things are white space sensitive. So now if we did the head command to take the first 2 rows of our file name and then pipe that to the tail and select off the last line of the first 2 lines, done. And that gives us the right answer. Now I'll walk through this one line command, this command here. So notice the $. So in Bash, the $sign is what references a variable that's defined. So here is the loop variable file name, which is going to iteratively take each of the .dat files in this list as it goes through the loop. And the $ file name is how we reference that file name inside the loop body. The loop body is everything between do and done, basically. Okay. And if I press up, notice that Bash has kind of nicely translated this multiple line loop into a single line command for me. And if I hit enter again, it would do the same thing. So let's refer back to okay, so follow the prompt. So I explained about the differences between the prompt. So the semicolon can be used to separate two commands written on the same line. So that's why when I pressed the up arrow, it converted this multi-line loop into a single line loop where everything was, where the individual lines were separated by semicolons. So that's another. I talked about the loop variables. So, you might be tempted to do something like this and say for x and, using x as a loop variable, but file name in loop variables, it's useful to give them a meaningful name relative to the context in which you're working. So if you're looping over files, then file name is a great name for a loop variable because it represents, exactly what that thing is as you're looping over it. It's a file name. And that's what you're passing in. You're passing a file name into the head command. And obviously don't do something like this, where you're passing in a looped variable that is completely meaningless within the context in you're operating. Even though this would work. Like both of these two examples here would work and execute fine. But again, it kind of context matters. Okay. So looping over files. So let's take take 5 minutes and start looking through these exercises a little bit, and then I'll pick one and we'll go through it. We'll go through it together. So I'll go ahead and set timer now. And yeah, just take a look. Obviously you're not going to get through all of them in 5 minutes, but maybe pick one or two that look interesting and see if you can get through them in the next 5 minutes, and then we'll do one together. And then in the meantime, I will be right back. Okay, I'm back. So there's a question in the chat. So here we use head and tail for horizontal line. If there would be a vertical column and we want to put it in a text file, which command to use? So I believe the command is cut. And there is an example of exactly this kind of operation in an exercise that we skipped. Yeah, here. So in pipe construction, so here you have this animals.txt, and you are going to cut using the comma as a delimiter, and the second column, I think, is the, or field is the way to think about it. And so basically this pipe construction and which pipe, so these two give you examples of a workflow where you're basically extracting a column from a CSV file and doing some processing with it.
What is D and F?
So if, so I believe D is short for delimiter. So let's take a look. So if I do cut help, so yeah, so D is the delimiter, and then F is the field. So maybe I'll just do this exercise. I'll just do this exercise right now. So so it's on the using this animals.txt file. Okay, so we want to, I think I need to go up one, or maybe I didn't. Maybe it was in the data folder. There it is. Okay, so if we cat the animals.txt, so here this is like a little CSV file. So the first column is like the timestamp, and the second column is an animal, basically. So the command was something like cut -d space comma. So it's a comma delimiter, followed by space, followed by another option, field, which is what field is basically a column. So the first column, so 1, the second column 2. So if we wanted to extract the second column from animals.txt, we would do that. So that's kind of how that command works. And then we could pipe that. I think the idea was if you pipe this, if you first sorted this, and then piped it to the unique command, then you would get an alphabetized sorted list of unique animals, something like this. But the relevant part, based on your question, is this cut command. So you could use this cut with if you were using a CSV file, then the -d comma would be the same, and then it just depends on like what column do you want to cut out. And I think you could cut out, you could pass in a list here. So for example, I mean, this file only has 2 columns, but if I was to pass in 1 space 2, then I know that didn't work. So it said you could pass in a list of columns, but then what is the syntax for the list? So here it says fields equals a list. Select only these fields. So maybe I've forgotten exactly what the list syntax is. Yeah, no, that's not right. Maybe it's this. Yeah, there we go. Okay. So then you could pass in. So here, this is basically giving me the same file back because it's only because there are 2 columns in the file. But I guess I could do. This is how if you needed to cut out multiple columns. So if I did 2, if I did this, that's giving me the same. Okay, so that's not quite doing what I was thinking it might do. But anyway, I think you get the idea. How to use the -d with a space. This is a good question. So I suspect that you could do D with that, I think, would do a space, I think. Let's see how I could quickly check that. So I skipped over it, but there's a way that you can use the less than operator to I think this might work. So yeah, so if I don't provide a file, then it's going to expect that I'm going to type something in manually. So now if I type hello world, so basically this is a shorthand for a space delimited file. And then I want to cut out the first column. So it cut out hello, basically. So that does work as expected. Okay. And the question about the default separator for cut, I don't know. What does it say? Tab. Tab is the default. Okay. Right. So that was a diversion, but an interesting diversion. But because we took a diversion, I'm going to skip going over the for loop examples. Instead, I'll just leave the solutions there for you to go through on your own. Because what I want to do is, well, I guess at this point, just kind of talk through the rest of this. I won't actually get to shell scripts. So now I'm going to just kind of talk through the rest of these examples. So we've got some slightly more sophisticated examples of for loops. So here we're looping over all of these .dat files, and this echo command is going to echo out the file name. So it will basically print this file name to the screen, and then it will run this command, which is first going to select the first 100 rows of the file and then take the last 20. So that's like rows 80 through 100, basically, or 80 through 99, I guess, to be more precise. Right. And the echo command is important because if we don't put echo, then it won't print the file name. Okay. So Rakesh is asking if we can arrange another time to go over the last 2 lectures. The short answer is possibly. It depends kind of on the level of demand. So I'll be sending around a feedback form for this workshop, so I can get some feedback on you guys about the mechanics of how this was run. This is the first time I've done a large scale kind of online training like this before, so I'm kind of keen to figure out whether or not there are any things that I can do better next time. Certainly if there are things I should avoid doing again. But there will be a kind of a free form text box. So if you feel strongly that you would want somebody to go through these materials, the rest of these materials in a session like this, then please be sure to write that in. And if enough of you think that that has value, then I'll talk to our leadership in the Research Computing Core Lab and see what we can do. So here's an example. I mentioned earlier about avoiding spaces in names, and this is exactly why you want to avoid spaces. Or here is an example of why you would want to avoid spaces in names. Because Bash, so much of Bash is space delimited, then spaces can turn into weird interpretations. So for example, if you had a file that was called Red Dragon and Purple Unicorn, and you tried to process those naively in a for loop, you would end up getting a break because they would pass red in as a file and then dragon.dat as a file, and neither of those exist. So if you wanted if you had spaces in file names and you just had to deal with it, then you would need to surround the file name in quotes. Or you can put the quote around the file name, and that will make sure that it is handled properly when it's passed into the head command. Actually, you need both of these things for it to be for it to work properly. Right. So there's an example here with copying. And a diagram of kind of explaining what's happening with the copy for loop. So if this was your for loop, whether it was written kind of interactively in the terminal or whether you put this for loop inside a script, just inside its own text file, then kind of this is what the process looks like. It starts and it picks up a new value, which would be this file name, and it's going to run the process, which is this command, and then kind of loop around until there's no more new values to process, and then it's going to end. So that's kind of the basic process flow of a for loop. And here, this for loop is using this echo command to check that it's doing the right thing before you actually run it. So here I'm taking the input file name and I'm copying it to a file called original dash, and then I'm basically prepending original dash to the file name. And by echoing out the full command, I can kind of see that this is doing what I think it should be doing. So it's taking this basilisk.dask and appending or prepending the original dash to the basilisk.dat, but it's not actually running a copy command. So then I could go back and delete the echo and rerun the loop, and then it would do the copy. So that's basically a way to use echo like a print statement to kind of check what you're doing before running everything. And I think I'll close with this example from Nell's pipeline. So we have all of these. So now I'm going to switch over here to my instance. And so we have this, we had these files earlier that we needed to process. So we have all these files, and earlier we worked out that the files that we needed to process were the files that matched this pattern ends in either A or B dot txt. Yeah. So now we understand the basic idea of a for loop. We could do something like for file name in star AB txt, Now, just going to make this a little bit smaller so it'll fit on one line. And then I'm going to do, and then I'm going to echo the file name. Done. Okay, so all this did was basically echo out the file name. So that's fine. Okay, so the input for this GooStats program, that is like this, the placeholder for this stats program that she's going to run on these input files to generate output files, expects the following kind of setup. So I'm just going to my browser is now seemingly gotten tired. Okay. So I'll go in here and say echo GooStats, and then this is no good. So I'll do for file name in star.ab dat do echo GooStats, and then the input file name, and then it expects then the second argument is actually the output file name that you want, and we'll say stats file name. Okay, so this did not do what was expected, and why is that? Aha, exactly. Wrong file extension again. That's the second time I've done that today. There. So again, this still haven't done anything. All it's done is printed out the files. There we go. All right. Sorry, things got a little crazy. So then what I can do is, once I'm happy that it's doing what I want, I can go through here and I would just delete the echo. And why? Because there we go. Okay, now this seems to be doing something, but I don't know if it's doing the right thing. So because the computer could be stuck in stuck somewhere. It's not clear, right? Because I've not basically set a print statement anywhere that would kind of indicate that actually this loop is making progress. Now it looks like it's finished. So okay, so now I have these text files here. So it looks like it worked, but a better implementation of that loop would have included a print statement to indicate that I was done processing a file. So maybe one way to do that would be, first let's remove all of the files that match stats star.txt. So now I'm back to here. So then if I went back and I took a look at this for loop again, but then I added another line, which was echo done processing I guess I should put this after the goostats. So I could come here and I could put something like echo done processing file name. And then hit enter. And so now I can kind of more clearly see that process is being made. Okay, I went through that last part pretty quickly. Apologies for that, but we were running a bit short on time. Now, the thing that we're not going to have time to cover today is basically, instead of doing all this manually at the command line, it would be better to actually write these for loops in a text file and called bash script, and then you would have a script that you could rerun rather than manually doing all of this from the command line. And that is what is covered in this last exercise, basically, which is how to take the text that we write at a command line, copy and paste it into a text file, and then run it like this. Bash, and then the name of the script that you want to run. And what? We don't have time to cover that. Okay, so just to kind of wrap up. So first, thank you guys for turning out today. We had a large group of participants, and I will be sending out a feedback form either later this evening or tomorrow. And please do take the time to fill out the feedback form. The way that we are kind of going to take attendance for everybody who came is depending on who returns the feedback form. So if you did invest the time, the 4 hours of time to sit down and go through this material together with us today, please do take the extra 5 minutes of your time to fill out the feedback form and submit it. We will be keeping track of kind of who attends, and we're looking into issuing kind of a certificate of completion to those individuals who attend all of the sessions of the Introduction to Data Science workshop series. And also I know IBEX and Shaheen, KSL colleagues, are treating courses like this as useful prerequisites for IBEX 101 and Shaheen 101. So they'll also be interested basically in who's been attending these trainings. So the recording, I'm going to do a little bit of light editing on the recording. I'm going to try to chop it up into distinct episodes as much as possible, and then I will send them out on YouTube, and we'll send around the links to make sure everybody is aware of them once they're available. So if you want to rewatch or go over some of the instruction that we did today, then you can do that. Or if you joined late and missed the first half or something like that, then you can go and rewatch the relevant episodes on YouTube. So with that, I'll hang around for a few more minutes in case anybody has questions or wants to chat about things. Otherwise, thank you for coming. I look forward to seeing you in the rest of the Introduction to Data Science workshop series.
Hi.
Hello.
Can I ask a question? Random
Sure.
question. First, thank you for the very nice lecture. It was very informative. I just had a question. When you were echoing the file names before you pass them into the software, the stats one, isn't this a bit expensive in terms of time? If you have like thousands of files, this will slow a bit the process, no?
Sure. So I mean, like the print statement is basically there solely to kind of make you confident that the loop that you have written is working properly and actually making progress through the files that it needs to process. And what I would do if I was prototyping a workflow like this is if I had 1 million files to process, I would write a loop that only looped over like 5 of them, and then printed out the the file name as it went for those 5, just to make sure that it was working properly and doing what I was expecting it was going to do. But then when I went back and ran the analysis on the full million files, then I would probably delete the echo print statement, because it would basically just print out to a log file, and it's not really useful to have a million lines of file names in a log file. So I guess the short answer is yes, you're correct, and you could remove it once you're confident that the loop is working properly.
Okay, thank you so much.
You're welcome. So I see that there's a question in chat. So why did you add bash on the loop? That was because of the way that the GUStats program, which is basically, I think, a glorified Python script of some kind, is supposed to be run by bash and not directly. Not directly. I think it mentions this. I'm just looking now through the loops, the loops episode, because I think it mentions this. Yeah, that's basically why, is that bash is the program that runs the GUStats, which is basically a script that takes input files. I guess I could just check this really quickly. Yeah. Will awk be covered later? No. So awk is not something that I cover. There is a really nice book called Data Science from the Command Line. So if you really want to get into doing very sophisticated things with command line tools, then there's this interesting book called Data Science at the Command Line, which it's getting a little, there's been a new edition. So I was going to say it was getting a bit dated because it first came out in 2014, but it looks like the second edition is in development. And so if you want to understand how to use awk and sed and some of those things, then I would recommend taking a look at that, because it covers everything. Are you going to talk about the alias command? So the alias command is covered in, there is an episode on the alias command in the shell extras, Software Carpentry shell extras. So I don't teach the shell extras directly. There hasn't been, in the past, too many people asking for that type of material. But please note on the feedback form, if that's something that you would find interesting or useful, then please do mention it. And again, I'll pass it along to my leadership, and depending on the level of interest and our other priorities, we could think about having basically having an advanced shell course that would cover. Basically, I would teach this shell extras material. we've still got 14 people hanging around here, so I will hang around until the last person leaves. So if you are hanging around because you have a question, that's awesome. You know, ask your question. But if you've just forgotten to leave, then yeah, please feel free to leave whenever. We're done at this point. I'm just kind of hanging around for anyone who has questions. You're most welcome. Thank you for taking a Tuesday afternoon